yes, we can be selective about the capabilities, but when we allow a capability, we also might have to have other mandatory access rules like mount or something else, because we have finer grained than the capability. So we'll have the capability things, right? So this is a video, and I don't know why it starts with black, because the screen is not black. Whatever.
Yeah, because this is why I did this.
So this is
again, it's
KDE not crashing.
Yeah, exactly.
And so
we have the notifications in level and scalability, but it's on the process.
So what's happening here is it's getting denied. We thought of that. We're transitioning to the user namespace profile. The capability of being denied. What's happening is the sandbox then comes out of the user namespace, and it basically it downgrades. Either it's not using the sandbox or it downgraded how it's trying to do the sandbox. So it downgraded gracefully. And then deny, so denying user versus denying capabilities. Applications have different error handling. It's very application specific. Some of them work better than one, some of them work better than the other. But overall, allowing the user namespace and denying the capabilities causes less crashes. Part of that's because WebKit's embedded in some of the things. Chrome,
yeah, and you cannot make a singular electron profile or stuff like that.
I don't want to either.
Yeah, both. Okay,
so now what are we going to do? We're going to, by default, we're going to have them define things like train. We're going to block them from unprivileged users. Privileged users can still use them. They're still restricted to all trusted only applications, but now we're a little finer on whether we allow the user namespace or whether we're going to negate the capabilities with it. Undefined is going to transition, is going to allow the transition to the special profile. If that special profile is not there, policy-wise it doesn't have to be match the state. So it must be, the child must be.
Tu me docker s'attaque
Sandboxing just looking at the child if it isn't a profile, so if come back, if it's undefined, if it isn't a profile, it's blocked. There's a profile, in a few special cases, a profile allows capabilities for collaborating that can't condition based on certain things. But it's special. There's gonna be some things. So then we have what do we know for say unshared profile, right? It's something that's stored here is very generic. Point being is that transition is
Is that the one I was yeah, I think I was that was the one that was just like it said it just shows the transition of it.
actually we should be stacking it. We'll go back and fix that. We should be stacking it. So having a reroute profile. That's fine. So what this shows is, we actually have to treat reroute differently than calls from define. So the point being is there's cases where you can't just go straight. I'm not going to allow this hierarchy down to everything for protection. At the distro level, we actually have to, we're selectively allowing, there's different cases and different transition types we have to make. And that's a general principle. It's not just for file or local app. It's that piece for more trusted and flat. And we use because we're running against a dev, we can do this. A dev can do we'll install this policy set. Instruction. So we have integration tests, right? Integration testing for that.
Oh, no, he's here. It's just,
And then
he doesn't.
you get to the last one, which is just understanding the state patch to make it easier for users, but
Well, I just figured if
summary.
I wasn't applying everywhere
So you're gonna stop. Where are you gonna stop? Assumption.
Assumptions. So, whatever was taken. No, sorry. Here. Does that make sense?
That works.
Because the introduction is still what is the introduction, so the basic mechanisms and function technology. Basically, we can do this.
Did you want me to do the CP slide? Or do you do that? CP was that the details there.
Yeah, okay.
So I'll step in.
Was it on? What happens? Why is it?
Full screen.
Okay. It's good.
There you go.
Good morning, everyone, again. Welcome to the second day of Linux Security Summit Europe. Very good weather today, so I'm hoping that people still stick for a while to our program versus like going and exploring Vienna. I think we have still interesting program today. We did have some BOWs yesterday. I think they were pretty good. We do have time also for BOWs today, so if you're interested to schedule a BOW similarly like yesterday, write the BOW, you know, the title, the theme, and the contact point to the board outside. So again, this room and the room outside can be used for the BOWs at the end of the program. And I just want to thank everyone for attending with our Linux Security Summit Europe this year. And thank you very much for Linux Foundation, and especially to Jennifer, who I think is currently stepped out, but for organizing all the practicalities and running this. So, and of course to our technical program committee and the sponsors. And I just want to remind the speakers, please try to repeat the question from the audience, because we don't have a mic and it can be difficult like at the back to hear the actual question and get the context. So I think with that, let's move to our first speaker. So please go ahead.
So we're going to discuss the unprivileged user namespace restrictions that landed in Ubuntu 24.04 and has been a source of problems for several people still. We're still working on cleaning it up.
Okay, so I will begin by introducing what are actually user namespace. I'm sure everybody is familiar, but just to make sure. So user namespace is a way to isolate security attributes for groups of processes. So you can both do user ID, GID, but capability, security, but any security attribute. The interest is that different namespaces will be able to have identical, for example, user and group ID, and that will not trigger conflict. So in a namespace, the processes can be root, and it's a regular user in the remaining of the whole system. So this was designed as a basic for containerization. So that's great. User namespace have a lot of valid usages, but there is a problem, and the problem is that it increases a lot the attack surface. So how do we do to reduce reduce this, and namely how to allow a privileged user to how to use a user namespace for a privileged user. It can be a problem because it can bring a lot of security issues because you then have access to the whole kernel surface associated to user namespace, and normally that's root only. So basically, medium priority, for example, it would be only applicable to root for vulnerabilities. Then it's applicable for every processes, and it can really increase the attack surface.
We get asked often, is it really a problem? And the answer is yes. This is a subset of the CVEs that have been used with user namespaces, and it's actually a lot worse than this. For Ubuntu, like say Pondone, we've been participated in that for the last 5-6 years. Every year, they've been used to own us. In 2024, all 4 exploits that owned us used user namespaces in their attack chain. 2023, 4 out of 5. Google estimates that 44% of exploit chains are using them. And if you think about the kernel at large, like syscaller is reporting roughly 1,000 plus bugs a year. Now, not all of those are exploitable, and of the exploitable ones, There is a subset of those that are exploitable to user namespaces, but we don't, we have the ones we know that are exploitable, we have the ones we know that aren't, and there's this whole whack of ones in the middle that they need a lot more analysis to know whether they are, and that, from a distro point of view, makes it so we have to treat those as higher priority than we might otherwise. If it's not exploitable by a regular user, it's, it's something we've fixed, but that's different than the privilege escalation that a regular user can use to exploit this and get, root access.
So let's state it differently. What we want to actually do is to prevent untrusted unprivileged user or code base to use unprivileged user namespace to attack the kernel. So the thing is, we don't want to totally disable user namespace because, okay, that could be a solution, but it's used pretty everywhere, and we want trusted code to be able to use them. For example, Firefox or Chrome rely on them to make their sandboxes, and just blocking user namespace wouldn't make real sense because it would actually reduce the security for this application. Because in this case, user namespace can actually be used to improve the security level of the application. So the problem is not with unprivileged user namespace per se, but because well configured can be good, but we want to restrict it without breaking too much. So yeah, the thing is make unprivileged user namespace work without breaking the whole world. So, okay, the first solution that is possible, and it's to some extent used, is to restrict the user namespace creation. Okay, that's something that can be enabled by default in the kernel, and then with this restriction, only trusted application, for example, my Firefox, or any application that I know uses unprivileged user namespace correctly, can access and use this feature. And these are the only ones that can create unconfined process. So here, unprivileged user, like unconfined, cannot create user namespace. So for example, unshare will not be able to create user namespace, but privileged user will be able to do it. And because we want the user to be able to choose, there is a global policy variable so that we can choose whether we want to enable it or disable it for the administrator. So here is a video about a crash of KDE. So, okay, I will try to add a widget. So the widget actually uses unprivileged user namespace to work, and then it crashed the session. Okay, we have about the terminal remains active, so we can type command. But if I try to click on the user interface, it's unresponsive, and even if I log out, I won't be able to log in. So I broke my machine basically. So yeah, that's a big issue and can be really annoying. Oh, sorry. The thing is, it's not the only one. Like, there is a lot of application, and you can see here the list of bugs that were reported to Ubuntu, which is a huge one, and a lot of bugs. So we can create profiles, but like if we don't do anything, many applications will break badly. So yeah.
And so the breakage on those applications, all those ones under there, that's one of many bugs, is not just a regular breakage. They're dying with sig trap, sig seg fault, those type of things. So it's a really poor user experience.
So yeah, how does the user namespace are created? Let's take a step back. So basically, I am an application, a regular application that is in the system user namespace, and I will unshare to a new user namespace. So I have my application, which is in a new user namespace, and then I will drop privileges to have something safe for my code. The thing is, there is a way to attack because there is a time window where you can attack, and you are actually not privileged, but the code that is executed is actually don't know. For example, for unshare, the attacker can execute anything, so he can, for example, not reduce his privileges. So it's basically a strong way to attack. So the same thing works with clone. So I can clone, and I have a new application, and similarly, it is possible to attack. There is something similar for setNS, but it's not exactly the same because it's privileged, so it's not under the scope of this presentation. So how to block it? There is two ways. We can either block the unshare, and that's what I showed. So the privileged user will not be able to make this unshare, and it's okay. There is another way to protect it, is to let the user make the unshare, but then the new application will be restricted by default into a profile file that will prevent him to make capabilities. So that I can use the user namespace, but then I cannot make privileged operations, so I reduce the attack surface. And the same thing for clone. So there is two options. These two options have both advantages and drawback. Just blocking the user namespace is simple to understand. Well, you can see that it is denied, but the thing is, it will break a lot of applications. A lot of applications need this, so, and for the user, it can break unexpectedly, and you saw on the KDE example that it's not that easy to understand that it was due to user namespace. And the other way to do it is with capabilities, and then a lot of applications will still work because, for example, some Electron apps have either don't need capabilities or need them, but have a fallback mode. So in the video, they will still work even if it was not possible. The thing is, the user may not understand that a capability denial was actually linked to user namespace. So, yeah. And yeah, Mac rule can require more rules. So just to show an example, so we do the same demonstration than before. The difference is that we block capabilities, and if I try the same thing, it will actually work. So I was able to open the window, even if I had a denial. So yeah, I went to unprivileged user namespace here, and so I made the transition to unprivileged user namespace, and then I check the capabilities, and it was denied. But because KDE has a fallback mode for this, it was able to gracefully fall back, and there is a lot of cases where it's the case. So it's not planned to have a user namespace denied, but in a lot of cases, if the capability is denied, well, we'll have a fallback mode, so the crash will be less horrible. And I will John go on a second solution about the denying capabilities.
All right. So instead of the simple just block user namespaces, we're going to use a kind of a hybrid approach. We're going to block user namespaces. We are going to also work with capabilities and not just capabilities. The LSM's finer grained than that. It's all privileged operations. So again, anything that's using user namespaces has to be in a profile that's going to confine it and restrict what it can do. Policy is going to mediate the user namespace. It's going to mediate the other privileged operations. The unconfined, if you know AppArmor, we have an unconfined concept. So it's going to, when it tries to execute code that has user namespaces, it is going to transition. This requires a small patch to the LSM that's not upstream yet. It's basically taking and removing a const keyword. So it's going to transition to a special profile that's going to deny privileges, anything that has higher privileges, like capabilities. And then we have again a global policy variable. Now, again for admins to be easy for them to disable. And one of the tweaks that was made, and we'll get into it later, was it's actually, while it's there for policy, we're not actually enabled in the kernel as default. So this is going to be something that policy is going to set on boot. And it makes it easier and we made it easier for admins to do this who aren't familiar with AppArmor policy. But we actually used a syscontrol to be able to toggle this Boolean, which is very similar to what was done in the past to disable user namespaces, if you know the big global toggle, which we still have. So the unprivileged user namespace profile, it's going to allow a set of things. It's going to have some things that it's denying and saying when on exec, when I hit something, I'm going to also, or not on, I'm just going to transition my policy. So profile layout with the user conditionals, we have kind of two options here. We can have a big giant profile that goes, it's used throughout the life cycle of the user namespace. Like you've got it at the application before the user namespace is created. It remains on the application during the user namespace privileged operations and remains with the application even after the application drops privileges. Now, this is not ideal and is kind of what we were stuck with without being able to transition at user namespace creation. Ideally, we could have different profile, different confinement for each stage of that application, right? So pre-user namespace, you have certain confinement. During user namespace, where you have elevated privileges, you have a different confinement. And then post, you have a third confinement. This would be optimal. Dropping privs with user namespaces is not something that is friendly to the LSM right now. So we don't have, we've played with this, but within the LSM itself, we don't have any way to properly say we're going to take this and drop privileges and let the LSM know. How privileges get dropped is there's a set caps, a set pcap, whatever. That's part of it. There's also other things that are done, like say setting no new privs, and it varies on application. We actually need some kind of hooking on the LSM to enable us to actually make those transitions. So we're ending up with right now a slightly less than ideal solution where we're going to have policy for something before it enters the user namespace, and once it enters the user namespace, it's going to keep that policy, and we're going to somewhat trust that the elevated privileges of that user namespace, it's gonna do the right thing and drop privileges. Now this is within the process. This is not when it calls out and executes another process. We'll get to that in a minute. And the reason we want those separate profiles, instead of like, say, the first case where we said we could conditionally allow capabilities, which would be the left side here, where you say, you know, if we're in the user namespace, versus the right side where we're doing a transition. There's a few things we can do if we do that transition that provide better minimum privilege, least privilege. One of those things you'll see there is we have an IPC type rule where you're using Unix, allowing Unix sockets to somebody else, right? To some other profile, some other application. In the conditional one, we actually can't properly separate that out. We want to be able to say C can talk to the application if it's not hit those elevated privileges, right? And we want to be able to introspect the process as well and say, has it hit those elevated privileges? Which the transition gives us, the conditional doesn't. So we get a little bit better if we do this transition than just doing a conditional. So it's just the regular, you know, what we're doing is this, what we were talking about before is the application starts up, it's got a profile, it's got whatever its privileges are, it clones, that clone creates a new user namespace, but it also gets a new restricted profile of some kind. And this is defined by policy, so we're very flexible about how we can do this, whether we're gonna allow the user namespace and deny the capabilities, whether we're gonna just deny the user namespace. And for applications like Firefox and, you know, that are using it for their internal sandbox, that's pretty well enough, right? But now we have, in Linux, we have a whole bunch of sandboxing applications, right? They are applications that launch other applications. And some of them are friendly and cooperative with us, and some of them are not. And what I mean by that is some of them will allow the user to, you know, they will keep the capabilities entirely within the application. We'll get to that in a sec. Others do not, and they allow all kinds of fun escapes. So say we have the sandboxing application. We're in the second phase here where it's created its user namespace, and it's doing the right thing. It's going to drop privileges, and it does an exec. We get a transition. Now that new application, it inherits the user namespace. It's in the user namespace, but we've got a profile around that application. It doesn't need access to anything. Everything's good, right? That case is good. We got the next case where we got an application, a sandbox application that is not going to drop privileges, and this is done in several of them. Unfortunately, or it can be an option. So it's like, well, I'm going to pass the option that I'm not going to drop privileges, right? And in this case, it does an exec, and that application now is in a privileged user namespace. It can issue those syscalls that, you know, I'm going to require capabilities. The capability check in the kernel passes, and so now I can attack the kernel with this, right? So this, if we didn't if we allowed this application to go ahead and do this exec, why is that not going? It would allow an attack. So you could use that sandbox application to bypass the restriction, and we don't want that, right? It must be confined. The sandbox application must be confined. Its children must be confined. So they cannot actually bypass the restriction. Now that breaks some use cases. We're going to block that right there. If it's trying to run something that's unconfined, it has to be confined. Now we can, and we do with those, define a profile that you're just going to get. You're going to be confined regardless. But for things that don't have, if the application that it's calling doesn't have a profile, it will get one that we're forcing on it. If you have a profile, we'll run it with that profile. So again, it's confined, it doesn't have access. Even if the application didn't drop privileges properly, that is the sandboxing application, it's still confined, it can't attack. And in the case where there is a few cases where we want to allow that escape. It's very selective, and again, but the policy is defined in allowing it, and it's there already. And it's only if it already exists and this exception has been called out. Unfortunately, it's needed in a few cases. So this is just kind of like the base idea behind the unshare profile. It's very broad right now. We're going to allow as much as we can, and all we're really doing is we're going to transition to a special profile when we call our child, right? And the child gets a different profile, and that profile doesn't have the broad privileges. Same idea kind of happened with BRAP, where BRAP is doing a little bit more. It has to do a little bit more because bubble wrap will use no new privileges, and no new privileges tickle some things in the kernel differently that can trip things up. So there's an extra layer there that's not to be worried about. It's doing the same basic thing. It's just dealing with the no new privileges. But if we just did straight up bubble wrap profile like that for confinement, well, bubble wrap will break Flatpak. And Flatpak, well, if you know Flatpak, you know it's using bubble wrap for its confinement story. But it is actually not a great citizen there, unfortunately, it turns out, because there is cases where Flatpak allows bubble wrap to do things it really shouldn't do. But it comes down to, we need bubble wrap when it's called to be called differently when we hit Flatpak. So this is one of the things we've run into, is we can't just have a simple, we're going to use bubble wrap, and here's bubble wrap's confinement. We actually have to have different use cases and say, when bubble wrap is being used from Flatpak, we're going to do something different than when bubble wrap's being called by a regular user. When bubble wrap is called by Steam, well, it's pressure vessel in Steam, but basically bubble wrap. Again, we do something different. So there's cases where we come around, and to make this work and not completely break the world, we have to be able to have unique situations that we can call out and enumerate. And so this is, if anybody followed the capabilities stuff on the LSM mailing list, why I said that just doing it at the capabilities level isn't sufficient. It gives you an inheritance hierarchy that's great for blocking all the children, but it doesn't handle the broader case of, we don't want these actually enabled by default and let any user use them, at least at the distro level. But that is what the standard Linux is now. And there's no way for the capability model that is, we're going to follow the Linux capabilities and just take it away and then the hierarchy down will work for all these situations. So Flatpak, like I said, it does define its policy, and Flatpak is responsible for making the policy. So it's not like the user can just pass any options to the bubble wrap command, but it still actually does let some applications run with privileges at times. We still have to look into this. And general principle, this is a general principle about not just bubble wrap, but all of these sandboxing commands, is we have to deal with special cases. Snapd is a little bit better citizen than Flatpak for really two reasons. But it's the same kind of story. So Snapd 1, this is one of the advantages of a closed store, I suppose. The applications they have to go through review. They have a declarative policy that they set up. And so when the application is allowed things, and Snapd added what they call an interface for use of user namespaces. And it's a privileged interface. Applications that want to use it have to go through review. So what it comes down to is Snapd isn't going to let anybody add anything, and it's hard to sideload stuff on snaps. Where Flatpak, one of its virtues is it allows, the flat hub, and allows people to put whatever in. But again, when you're trying to block these, it becomes a vector for people to just bypass the restrictions. So what are some issues we've hit, right? Out of archive code, there's a lot of applications that are not in the archive. I mean, we have a huge archive. We have, I don't remember what it is, between main and universe, we have 50,000 apps, something like that. But there's actually an awful lot that aren't in the archive. And we can ship policy for some of these things that aren't in the archive, or we even have versions in the archive, but then there's upstream versions as well, right? So if you think about Steam, we ship a Steam, and it's shipped as a snap, but most people are using the Steam client straight from Valve. Firefox, same idea. We ship a Firefox, but there's an awful lot of people downloading Firefox. So we can ship profiles for well-known ones like that, but we can't ship it for everything that's out of archive. Applications that have user-writable locations. If you have a user-writable location, somebody who wants to attack the system and use user namespaces, they can just, if you're allowing running something confined and access to user namespaces as a user writable location. So say a user puts it in their bin folder, right? And says, I'm going to set up a profile for that. Well, an attacker says, well, that location's not protected. I can overwrite what they put in their bin, and now I can run and use user namespaces and attack the kernel. So we can't allow user writable locations, at least at the distro level, right? We can allow users to selectively enable that on their systems, that they're taking the risk then, but really it's not such a risk for just the user because it's not something an attacker or an application really can expect then, right? App images. If you know anything about app images, this is where they run, right? Most people have app images, they download them, and they run them straight from their home directory. So does this break all app images? It doesn't, right? But if you know anything about app images, there's an awful lot of app images that are Electron apps. Electron apps, they embed a web engine, and that web engine actually uses unprivileged namespaces for its sandbox. Now, ideally, we don't want to break that sandbox, right? That sandbox, if that web engine can be trusted, is good, but we don't know it. There's no way for us to know that at the distro level, right? So we have to stop that. We can't allow it. And it's really unfortunate. We had an interesting situation where we've also had upstreams, and this was not malicious, but a malicious one could do this as well, have tried to circumvent the restriction. So they have a bug, things are failing, they want to make it work. A solution gets passed around on the internet, and they're like, oh great, this is a solution, test it on their stuff. And they're like, great, we can do this. And so they have this bug, we've got a solution, and we're a deb-based package. Well, we can ship some policy in our deb, because debs can do anything, they have root privileges. So we're going to install some policy on the system that fixes our problem. Only problem is that policy they're installing actually allows bypassing the restriction for all users of bubble wrap. We need integration testing to make sure that those kind of things aren't happening, aren't slipping into the archive to disable the restriction at the distro level. And finally, well, users really do not understand. It's like, I just want my application to work. It worked before, right? And it's hard to say no in those cases. And so we have tried to provide a way for users to selectively disable and make it easy for users. There's a escape patch profile, a template that's been passed around that says, basically, this application can behave like it's unconfined, right? It's what it was before. There's restrictions not there. We're not doing anything, right? And it's an okay solution, but it's still too hard for users. We talked about a little bit about app images. Maxime's going to talk some more about app images. This way.
So yeah, for the average user, well, you don't understand what happened. you have a crash, and well, it's either a sick trap or a capability denial or something that, without being an expert, you won't know that it's caused by user namespaces. And also, most users are totally unfamiliar with AppArmor. So the way of shipping a profile can be a solution, but for most users it won't be practical. And just to say that, I have an Electron app that should work, and in all tutorial it worked, but then it didn't. And if I look on the mesh, well, I saw that I make the transition to unprivileged profile. But then, just I had a capability denial to unprivileged, to sysadmin, and then a sick trap, and the message is not really helpful. So yeah, sorry. So what do we want to do? If we have a user namespace that is denied, we want a way to make user-friendly notification so that the user understands properly what happened, and he can choose to whether to add the creation of user namespace or not for this program individually. So we want it to make to be as easy as possible. We don't want notification flooding, and we don't want it to be abusable by malicious users with a graphical interface that is integrated. So we do that by AA Notify. So AA Notify is a tool that already existed. So it runs as a background task, and it will show when a user namespace is denied. And we created new user-friendly graphical interface in the new version, so that the user is able to make appropriate actions to add he wants with an interface that is are tameable, so integrable in distros. So we pull notifications. We can filter operation to have only user namespace create, and we can show graphical notification for splash notification when something user namespace is denied. So basically, how it works when user namespace is denied, I will have a window that will tell me, okay, I have a notification. I can have more info on why it happened, what should I do, and if I want, I will have to type my password to allow it, and if I allow it, I'm able to run it. So I have a quick demo about this. So I will remove unprivileged user namespace to show straight denial because it's easier. I started AA Notify, so this software, and I tried to make a user namespace, which is denied. That is to be expected. Yep, sorry, I restarted the demo. Okay, so again, I start AA Notify. My unshare is denied, and a notification is displayed. So I can allow it, I type my password, and up, a profile has been created for unshare. So now unshare works, and I can check if I type my ID, I am nobody, so I am in a new user namespace. I was in a normal one before. So let me remove the profile I created to go to the back to the previous state, and I make a splash notification so that it's easier for the user. And then when I have a denial, I already have a pop-up screen that tells me what to do. I can have more information, and if I want, allow or deny the user namespace. And it will work.
So I User applications are not the only issue. LXD is kind of like sandboxing applications on steroids. So LXD, because of what it's trying to do, right now it just goes through and it's disabling user, if it's installed, it disables user namespace, well not installed, if it's running, it's going to disable user namespace restrictions globally. And that's unfortunate. We need to fix that, right? Well, every policy, every container with LXD actually does have a policy namespace. With old contain, and there's potential to do something here, right? We don't want the restriction necessarily being applied to old containers because that would, you know, break the old container. Like policy on a 2004 system has not been updated to account for the user namespace restrictions. So if you're running a container against our kernel, you know, a new kernel, and it's being applied, it's going to break. So running containers of older operating systems does allow bypassing. Now, this is somewhat mitigated by the fact that LXD is, you have to have the LXD group, and that's basically root. And people aren't in that group by default. So what we have, you know, LXD, it's running a 2404 host, say, and it wants a 2004 container, like I said. We don't want to break that, right? Right now, without disabling it, we do. So with the kernel, like I said, it's available, we're disabled at boot, right? So the 2004 container, when it comes up on a kernel, if it's disabled, it's going to be fine. But say we do something different, right? Well, as I said, we'll get there. LXD, like I said, it's toggling it on and off at runtime. So that makes it so the 2404 container works. Unfortunately, say we bring up a 2404 container on a 2404 system, well, the 2404 container, because it has its own policy and there's a global toggle, right? It comes up, it's boot, it toggles that Boolean, it enables the user namespace restriction stuff in the kernel, and it ends up breaking the 2004 container. Because the 2004 container doesn't know how to deal with it, right? It's fun. So how do we fix that? We'll get to that. We got more fun though. We also use new kernels on old releases, right? We take our 2404 kernel and we put it back on 2204 to provide device support and stuff for those kernels. So it's not enabled by default in the 2404 kernel, so 2204 is not going to trigger that. So that works until, you know, we load a 2404 container on a 2204 host, and then it's worse than breaking one container, it actually breaks the host. So how do we fix this? We need to virtualize that variable. So instead of being a global policy variable, it's done at a policy namespace. LXD already cooperates. It sets up a policy namespace. This does require cooperation for the container manager. So if any other container manager was to use this, they would have to cooperate as well and set this up properly. So now if we virtualize on a 2404 host, we can run either. They both get their own set of policy restrictions. The 2404 container is acting like a 2404 with the restrictions enabled. The host is acting like the restrictions enabled. And the 2004 container has the restrictions disabled. Yes, the 2404 container can then be used to attack the host kernel, but that's the nature of using LXD. Same works if we take the new kernel back to 2204. The host comes up with the policy restriction disabled. The host is fine. The container manager sets up the policy namespace to have that restriction. The boots, the 2404 container works as if the container, as if the restriction's there, the policy works, and it doesn't break the host. So what did we learn through all this? It's a pain in the butt. We added confinement that allows various confinement that around user namespaces to over 120 applications in the archive. That covers just about everything that we know of right now, but it certainly doesn't cover everything out of tree. Like I said, we are shipping a few profiles for a few applications, special applications like Steam and Firefox that are regularly downloaded from a trusted upstream. We carry most of these special profiles or the modifications of profiles in a regular policy, but there are several applications that are actually carrying it as part of their policy. There's actually a lot in the KDE stuff, partly because how KDE embeds WebKit. Flatpaks right now are all treated as one in that count. We still need to do a lot of work to refine Flatpaks. In the end, Flatpaks are going to be a very large expansion on that. And Snapd, we're not counting Snapd. All the snaps that use it, they have policy that's generated, and there's not many snaps using this right now, but it's handled within Snapd, and it just works, and I don't know what the numbers are. So, you know, there's a security issue. It's not a perfect solution right now, but we can't allow user namespaces and have a perfect solution. As Linus said, when, you know, this got heated on the mailing list, we're stuck with these now, and we have to do what we can to make them work the best that we can. And we're still working towards some things to try to improve this, and like I said, experimenting with adding transitions at when privileges are dropped, for example. That's still going to take a fair bit of work to do, but that's where we're at the moment. Yeah, Paul.
Can you guys hear me okay?
I can hear you.
Okay. At the beginning of the talk, you were mentioning how you need to have a small patch of the LSM framework so that you can drop a constant. Is that for the user namespace creation hook?
It is. Yeah. So Paul's asked if the small patch to the LSM that's needed is to the user namespace creation hook, and the answer is yes. And I have that patch. I just have to send it up. And
quick question about that. Is that because you want to modify the capability sets in that hook?
no. Okay, so Paul just asked if it's because we want to modify the capabilities. And the answer to that is within the user namespace LSM hook. And the answer to that's no, we don't. What we want to do with the user namespace hook is right now it sets the cred as const. And this is during the cred creation phase when the cred's actually not in use. You saw this actually with the capability patch set as well that's been floating around. All the patch to the LSM does is change that so the const is not there, making it valid for us to change the cred in the hook, so we can update the AppArmor context on that cred before it gets attached to the process. And then where we're stuck right now is I just need to finish up cleaning up the AppArmor patch that we're going to send upstream with this one. There's a split there that there is some other stuff we want to do after follow on that needs further stuff, but a clean first patch to get that into the kernel is where we're at, is what we need. Any other questions? All right, thank you. Here we go. Take that.
I'm early. It'll take another minute or so until the talk starts, I guess. Okay, thanks. Hello. Hi, my name is Günther Noack. I'm from Google Switzerland, and I'm going to present today on Landlock. First about me. Wait a second. Does this work? Yes. Okay. I'm interested in computer security for a bit more than 20 years now. I've been playing around with this for a while. I work at Google in Zurich, and I'm a Landlock contributor since 2022, and I'm also the maintainer of the Go Landlock library, and in my free time I like to run and swim. So the outline of the talk is going to be, I'm going to talk briefly about the motivation for why we're doing this. I want to show you that sandboxing should be fun, and also that it's going to be, should be ideally maybe also be done by software developers rather than just by Linux distributors and system administrators, as we've seen in other talks today. I'm going to give a technical overview for those of you who aren't familiar with it yet. I'm going to talk briefly about the ioctl support that we added to Landlock over the course of the past year, and we'll then also talk a little bit about the delta of what happened since the last time that a similar talk has been given at LSS, and about the upcoming features that are planned for the future of Landlock in the next months. So, so first of all, about the motivation. As I said, I've been interested in sandboxing for a longer time, and around the time when I started to get interested in computer security, buffer overflows were a big thing, and as many of you are familiar with it, an attacker can completely gain access over an attack process and gain complete control over it. And then the compartmentalization of the normal Unix security model is things are compartmentalized between users, but not so much within the realms of what a user owns. So not the files of a user and not the different processes of a user. Those are harder to separate. And so what often happens is when an attacker gains control over a process, the attacker is also automatically going to have access to a bunch of other resources that are owned by the same user that is executing that process, like SSH keys, love letters, bank documents, you name it, company secrets. And at the same time, especially under the more traditional Unix tools with the small tools for a very specific task, tools tend to not actually need that many permissions, and the set of files that a tool actually requires is a lot smaller than that in many cases. And so what Landlock wants to do is to restrict the ambient access and to only permit access to those resources that are actually required. And in Landlock, that is not only files, it also extends to other types of resources. In this example here, I'm showing files, but it's going to grow a little bit bigger, of course. And of course, that is the principle of least privilege that many people who know security have heard about. And so I played with this for a long time, and one of the first things that I attempted was to use Systemd BPF. And Systemd BPF is this unprivileged mechanism where you can load a BPF filter into your kernel, and the kernel is going to enforce that for the current process and for the child processes of that process, and it's going to run like a packet filter, but filter the system calls that a kernel that the user space process does. And unfortunately, it has some drawbacks to it, and specifically the drawbacks are you can't follow pointer arguments like file paths into an open syscall, for instance, because that filter doesn't have access to the user space memory. But also at the more higher level, there is another problem with when you create a policy with seccomp and then you deploy your program and then you leave it there. And then maybe over time, some new kernel version gets rolled out. That kernel starts supporting system calls that you didn't know about at the time of writing that policy. And the same goes for the shared libraries that your program uses. This can also be the glibc. So what happens in practice is that your program that used to do, say, the open system call actually starts doing slightly different system calls over time. It starts using openat, and then it starts using openat2. And if at the time of writing the policy for your program, you didn't know about these, you're basically faced with the decision, there is a system call whose number you are not familiar with. Do you want to permit this? Do you want to deny this? And either way you choose it, it's going to be the wrong decision, because if you allow it, your program is going to have more privileges than it is supposed to have. And if you're going to deny it, you're going to break the compatibility that the kernel normally provides, right? The one that says any program should be executing in the future as well. So that is difficult. There are ways around that. There are very advanced mechanisms in seccomp where you can still do it somehow. One of them is, for example, that you statically link everything. You always make absolutely sure that you know exactly what you're doing, but in the big scale of things, it's not very practical for many programs. And so this is not so easy. Other mechanisms include SE-Linux AppArmor. We've seen a presentation on AppArmor just before this one. This is mandatory access control, so it's not done by the process. Solves a slightly different task. And if you put yourself in the shoes of a developer who writes an application that is maybe risky in nature or processes inputs from very dangerous sources, then maybe you want to also as a developer enforce a policy, and for that one, these ones do not lend themselves quite as well, especially because it's not deployed that widely and you are starting to rely as an application developer more on the setup that the surrounding system provides for you. So you need to understand a little bit where you're executing, and that is hard for software developers. Now, there's also user namespaces that I unfortunately missed to put on the slide. There was a great talk about that just before though, and I recommend to see that if you are watching this in the recording. And user namespaces also have their problems that make them difficult to use, and they tend to expose more kernel APIs, and actually they are used in a bunch of security vulnerabilities as well. So, okay, so now Landlock though is a new mechanism, relatively new, was introduced in Linux 5.13. It's an unprivileged sandboxing mechanism. That means it works like seccomp. It's the process itself that enforces this, and that designs the policy that is to be enforced. It is now the software developers and the processes that define what their security policies are, so it's more bottom-up. And we also support the backwards compatibility story better, so that you can actually know that in the future your program is also going to work. And finally, also, which is also a little bit different to seccomp, the abstraction boundaries at which you, like the level of abstraction at which you define what the policies are, makes a little bit more sense than in seccomp, where in seccomp everything is based on the system call numbers and arguments, and you need to keep track of what they are and how they change across kernel versions, and here you get a more stable interface than that. So, so the vision is essentially, we want to make Landlock simple for software developers to use, and this can be used to build sandboxing tools, but it's by far not the only use case, and actually we would wish that also many normal application and software developers start using this, and it is lightweight to use, so that people can use it in very simple utilities. Here are some examples. The ones that are in green are ones where actually Landlock was implemented. You can see, so pipeline tools that would be used in a normal Unix pipeline are classic examples where it's easy to use. They have a well-defined input, well-defined output. They do a bit of processing in the middle. So for these tools, it is often easy to apply. XZDEC is one of them. This is the from the XZ project, the decompression tool, where I will have a slide on this one later as well. But also things like Convert, that does conversion between media formats, also tends to be a use case where a lot of attack surface exists in the media processing libraries. And then also, netcat, ping, those are all things that could be used for that. And then Zathura, the document viewer, is unfortunately not the one that I'm using right now, but that one also supports Landlock in a future version. So I'm going to come to the technical overview now. Out of curiosity, how many of you have used Landlock in the past? Okay, that's a few already. About 10 people, I would say. So the basic architecture of how you would design your program that uses Landlock is this. You see in the initialization phase of a program, this is roughly the phase where you would parse your command line flags, and where you would parse your config files, and where you would interpret what the program is even supposed to do. That's the phase where you're probably processing input that comes from more trusted sources, right? The people who provide the configuration files, the people who provide the flags, they already invoke your program. So that by definition, they have at least the same amount of rights as you have. So that would be considered a more trusted source of input, but later on, maybe you have some more nefarious attacker who starts to provide input from the side, a media file, or maybe they can do HTTP requests over the network. And so you need to analyze a little bit, what is the inputs that you trust, what are the ones that you don't trust. And by and large, in the initialization phase, you have inputs that you trust more. So that's the phase where you would want to figure out what the policy should be looking like, and where you work in a more open, unconstrained environment. And after you figure out what the policy should be, you design a policy, you construct a policy, you enforce that policy, and then after that policy is enforced, the kernel is going to enforce the policy for whatever that guy with the hat is providing to you as input. Now, for creating and dropping the policy, the API that you would use looks like this. There are 3 system calls to it. One is called Landlock create rule set. Rule set is just the name, the Landlock name for what the policy, it's the policy essentially. And when you call Landlock create rule set, you will get back a file descriptor that represents your policy at construction time. Then you can add exceptions to the policy. So the policy says what is restricted, and then you add exceptions to that. And then finally, there is a step where you enforce the rule set. Now, to create the rule set, the system call is this one down here, Landlock create rule set. And there at the top, you can see I'm passing a struct, and it gets 2 fields. One is the access rights for the file system, one is the access rights for the network, and those are both bit masks of different operations, which I will show in a slide, a few slides in the future. And that would construct a rule set where the operations that are set in these bit masks are not permitted anymore under that policy. And then maybe you have some files though where you do want to see them and where you do want to use them. And so in many cases you would, for example, want to see your shared libraries that you load from user or from user lib. And so the way to do that is, after creating your rule set, you would open a file descriptor to the surrounding directory or to the specific file that you want, and then you add a rule with this landlock add rule syscall, and then again you pass a struct where you say what the file descriptor is, and then you say which specific access rights you want to permit on this file. And then this is added to that policy. And then finally, in the third step, this is the simplest of them, you just take that rule set and you enforce it. And after this system call returns, everything that your process does will be run by this policy and double-checked. And also policies can be nested. So if you enforce a policy and then you or your child process enforces yet another policy, it'll always restrict more and more and more, and it only narrows down what you can do. Now, the operations that are restrictable in Landlock, there are 2 main categories at the moment. One is the file system operations, and one is TCP networking. For the file system operations, this is, I apologize for the slide, it's very, very long identifier names here, but by and large we have 3 groups. The common operations on the top are those are the operations that let you open a file for reading, open a file for writing. Truncation is also one that we control explicitly here, and also for executing and also for reading directories. So those are very, very common ones that you would want to mention in many of these policies. Then there is a whole group of them for directory entry manipulation, about adding various types of Unix files. And then finally there is the one about ioctl, which is a little bit special, and this is the one that I will talk about a bit later. For networking, we have these operations. Here on the right-hand side, you see a very textbook example of the steps that you would undergo in order to establish a TCP connection. And we have 2 access rights that you can restrict there. One is for the bind operation and one is for the connect operation. You can see that if you want to walk this state transition from the top to the bottom on the client or on the server side, in both of these cases, you have something in the way that you can restrict. So when you use this, when you follow this schema to establish a client and a server connection, you can't do it if this is restricted. But there are some caveats to that, which I will get back to later when I talk about the future networking capabilities that we're looking into. So yeah, and then finally, the Landlock also has a backwards compatibility story, as I mentioned. There is a concept of ABI versions, so you can query what is the current ABI version that the kernel that I'm running under is supporting, and then it gives you back a number, and then you can have a lookup table on the side where you can look up which of these access rights already exists under which of these ABI versions, so that you know which of them you can use under the kernel that you're running under. And this can be used to build a best effort mode as well, which means that you can write programs that will run on any kernel and then use the most restrictive landlock policy that they can under the given kernel that they're running under. There are some smaller limitations. So first of all, Landlock is getting built incrementally. This means that many important operations are already restrictable. For example, you can restrict access to the file contents on your file system, but there are some smaller operations that are still missing. In the file system case, that is stat, so you can not restrict at the moment whether the sandbox process can see the existence of file names in the file system. And then there is a few things that are out of necessity also restricted. So if a landlock process would start to manipulate file system topology, you can see how this could potentially break the rules that you have added previously in your policies. So this is not permitted in a landlock process to do that. So you can't do a mount. You have to enable the no new privs flag on your process. That means that you can't use a suit binary, and also the use of ptrace is restricted. Yep. So now I'm going to get to the part about ioctl. So ioctl, as a small reminder, is a system call that is a bit of a additional mechanism if Unix read and write are not enough for you as an implementer of a device driver. And the interface is this. So you have to pass a file descriptor, you have to pass a number, which is the operation that you want to call, and then you can pass an additional argument as a pointer into user space. And it's basically a command multiplexer. It can dispatch to all kinds of implementations in kernel space, and they're mostly implemented by device drivers. An example would be the one here at the bottom, TOC-G win size. That one gives you the window size of the current terminal. So if you run that on stdout, it'll tell you how many characters in the X and Y axis you have for your terminal. And that's also where this traditionally comes from. So this, in my understanding, was introduced for TTYs actually at some point. So the motivation for supporting ioctl and Landlock is we try to apply the principle of least privilege here, and if the number of potential implementations that you can reach with the system call is so large that it becomes difficult to even for us as kernel developers to reason about what you can potentially reach with this, then this is maybe not something that puts you in a position where you can confidently say, this is what my program can do, right? So there is some desire to restrict that, also to restrict the attack surface. And so, yeah, that's the motivation here. So when we looked at the implementation of ioctl, we found this. There is the system call is implemented in fs-ioctl.c, and then there is a few ioctls that get handled directly at that layer already. So there are some, I would say, more trivial operations, such as manipulating the close and execution flag on your file descriptor that works through ioctl as well, not just through fnctl. And then you can manipulate the async and buffered IO flags for your file. And there are a few trivial operations for regular files, like asking for the file size. There is a whole set of operations that you can do on copy and write file systems for a reflink functionality, which means sharing of, like the per page sharing of pages across files, which is supported on copy and write file systems. And there are some operations on file systems, which is this is important to be precise about, because that means it's not this is not an operation on the file that you're calling it on, but the first thing that the implementation of this does is it looks up the superblock and then actually it works on the superblock. So that means this is actually an operation that works on the entire file system and not on the individual file that you're calling it on. And there is also a set of these. And then finally, if none of these is the command that was actually requested, then it'll fall back to the actual purpose of why ioctl exists, and it'll call that very generic unlocked ioctl hook. There's also a compatibility version of this one, which I omitted on the slides. And then it's up to the file to implement how that gets dispatched and how this is actually implemented. So we looked at some implementations of that, and so some of the implementations unfortunately looked like this. So you can see here, this is a bit simplified. I know I'm not doing a return at the end, I noticed that. So normally you have a giant switch statement in the middle, and then it dispatches to some implementation of this. But then in some implementations you will also find acquire resources step at the top and releasing resources at the end. This is often used for all kinds of locking or for memory allocation that is needed for all of these implementations. But there is this little problem with it that turns out if you're calling this with a command number that is not actually recognized by this device driver, it'll do the locking step anyway. And it'll do the unlocking step as well. And you know, when I say locking and unlocking, it sounds very, oh, this is probably not that bad. But reality is also, I found also some drivers where it's, you know, a few hundred lines of graphics driver code, and I can't understand this. So this is not something that we want to make it very easy to dispatch to by accident. So that was definitely a concern that we looked into. Now we thought about what should be the criteria by which users should be permitted to control the dispatching of ioctls and Landlock, and then of course the LSM hook for this one, which is here at the top, security file ioctl. It takes the same arguments as the system call itself, so it takes a struct file, which is the file descriptor in user space, and then it takes the command, and then it takes a user space pointer that is not really useful for making a decision. And then we thought about which of these properties can we use to control the policy. And then the natural one for us is, of course, the file path, because we already have pre-existing mechanisms, and this is the most uncontroversial part of it. Then we thought about, should we be looking at the file type, maybe? Turns out file types are not as granular as you would think. So there is some granularity that you can see from the struct file, but there is also a lot of anonymous files that are completely different things. And then there is a mistake that was made in SE Linux in the past at some point, where people thought, oh, we can use the structure of the command numbers because those get created with macros, and there's a read and a write bit on it, but turns out that doesn't actually describe whether that operation is for reading and for writing, but it describes whether the argument is being read or written. So that's also not something that you can use. And so in the end, to make that story short, this is actually, like, if you are interested in that longer discussion, you can read it up on the mailing list. It goes for months. But in the end of it, we basically came around and we said, we're going to make a very simple implementation for now. We're going to restrict ioctls only on device files, because this is where the largest variety of different multiplexed commands can get executed. and we're going to make it restrictable by file path. So that means that users are still quite through the file paths, they can still substantially control what actual device files they might want to have exceptions for. And finally, there's some very, very simple operations that we hand selected individually where we are sure that they are harmless and which we are going to allow anyway. And these ones are fioclex, fionclex, that's close on exec for the file descriptor. It doesn't actually touch the file, it only touches the file descriptor. Then fionbo, fioasync, those are the ones for controlling buffered I/O and asynchronous I/O. And then we have a few that we own that actually would not work on device files, and we only permit them for error code consistency, so that when you call it, you get back the right error code. This is one of the design goals that Landlock has, that you still somewhat execute in a more natural environment and don't get confronted with too many surprises. And then finally there is the set here at the bottom, which is the ioctls that actually work on the file systems. And we allow these ones because it would anyway be possible to call these ones. You only have to invoke it on the parent directory or on any other file from the same file system. Yes, this is kind of the same slide again, just in different words. Yeah, and yeah, so let's talk about the news that have happened in the time since this presentation was last given. So I referred to it earlier already. One of the surprises that came in March this year was that Landlock showed up in this attempt where people tried to put a backdoor in XZ, and they have in XZ manipulated the build tooling so that the check for whether Landlock is enabled or whether Landlock is possible to use, that check was not working anymore, and it would always say it's not enabled and it wouldn't build with Landlock support. So I'm just mentioning this on the side. I think it validates a little bit that we are getting in the way of nefarious people here, and I'm very happy about that. Yeah. Then another thing that happened was last month we had a bug actually that was a security bug discovered by Jan Horn, and I'm very thankful for that, and we encourage that people report bugs to us. That's why I'm mentioning it here. The bug was about a confusion of different LSM hooks where we did not implement one of the LSM hooks properly, which we should have implemented. It'll get fixed. It is already fixed now, and we're going to hopefully add a more comprehensive fix from Jan in the next months or for the next Linux release, hopefully, which is going to make that situation less likely that it happens to someone else. The next slide that I have to be careful because people have misunderstood the slide a little bit in the past. It mentions the name ioctl. It is not directly related to that ioctl feature I talked about earlier. So, and that is, while I was looking at this ioctl support, I realized there's another problem that Landlock has with ioctl, and that is there is a common ioctl that exists on terminal devices, and it's called tioxd, and you can use it to add characters to the input buffer of the terminal device, which means you emulate a key press. So if you think about what that means for when you run multiple programs at different levels of privileges on the same terminal, it's actually a problem, and it is particularly a problem for Landlock, because if you have a little Landlock tool down here and it has restricted privileges and it can emulate key presses, that means that it only has to add a few key presses to the terminal, exit itself, and when the surrounding shell takes over the control again, it'll read these key presses and start interpreting them. This technique was used in a long list of vulnerabilities for all kinds of sandboxing tools in the past. There's also a related ioctl called tioc-linux that made the same thing possible on the text console, on the textual terminals. And these ones, luckily, they got fixed recently. So it got fixed in Linux 6.2 by Case Cook and in 6.7 by Hanno Böck. And the fix is essentially that you now need cap sysadmin in order to use these features. And they have luckily not been used enough so that we were able to disable this. And as you can see here on the right-hand side, this is a screenshot from a CVE search engine. And you can see the red parts here. People are already mentioning that if these ioctls don't work anymore, then you can't use the exploit. So this actually works as well. Yeah. But these two slides about ioctls are not something that the Landlock ioctl support is really interfering with. So there is not that much relation with it, because in Landlock the access rights get enforced at the time of opening a file, but the terminal file descriptors you're inheriting from your parent, right? So they are already open, and that these policies don't apply to them. Now for the upcoming features. So we have two features coming up from Tahera Fahimi, who's also sitting in the room here. It's about IPC restrictions. So one is connecting to abstract Unix sockets. An abstract Unix socket is a Unix domain socket that is not identified by an address that is a socket file on the file system, but it is identified by an abstract name, which is a flat kernel global namespace of available Unix domain sockets, and that is a Linux extension to that system. And so for these ones, we want to restrict that you can't connect across different processes under different Landlock policies, which we call Landlock domains, and there is a nesting of these policies. So it should only work in one direction, so only from the processes that that you can't control processes that have higher privileges than you have. So this is going to be possible to restrict in the future. Same thing goes for signals. You also don't want to be able to signal a process that has higher privileges than you have. That's also done by Tahera. Then we have networking features that are coming up. So I showed this picture before. At the moment, we already support bind and connect. As you can imagine, this picture here is the TCP schema, how you would do things, but that doesn't necessarily apply for other networking protocols. So it doesn't apply for UDP. So we can restrict bind and connect, but at the same time, that same process then would be able to use UDP, or would be able to use Bluetooth, or you name it. There's a whole list of different networking protocols that are mostly not used by many applications. So the way out is, of course, that we restrict the use of the socket system call. The socket system call is also the one where you have to specify what protocol you're going to use. That patch is currently in review, done by Mikhail Ivanov. We have another one for listen. So as it turns out, what I showed earlier is when you walk down here on the server side, that state transition, turns out you can also open a listening socket without doing a bind first. And if you do that, you will get an ephemeral port, the same as what you would do when you do it as a client. And so it's still possible to open a listening server. And for that reason, we're also going to restrict the listen operation in the future. And that patch is also currently in review by Mikhail Ivanov. And there is another one that is not in review yet, which is also that was a bit of a surprise. This is also a Linux extension to the BSD socket API. It is actually possible to walk back in that state transition to an earlier state and then to reuse an existing socket. And that is done by calling connect with AF unspec. So when you do that with one of the protocol ports, with one of the sockets that use one of the protocols that support that, then it'll put the socket back into a state where you can use it for a new connection or for a new listening server. And that is, of course, for us potentially a problem if you imagine the use case where you're running a network server and then someone breaks into that server, and they're probably using a client connection to get into it, so they have a socket lying around, and if they were able to reuse that socket to disassociate it and to establish new connections, that is something that we don't want. So that's also something that is likely to be done soon. Yeah, and with that, I think the presentation is at the end, and I'm going to take questions. Yes?
In the last slide, the one you read, you should probably change that because I converted it.
Oh, I'm sorry. Yes, it says disassociate. I'm sorry about that. Yeah. It says disassociate this box here, and that's the operation that you would do to disassociate is to call connect with AF unspec. The man page actually explains it in the description section very much at the top. Yes.
Thanks a lot for the talk. I was interested in Landlock, now I know a lot more about it. I did some searching on the API level. I saw that there's already a Rust wrapper.
Yep.
So now the question is, with all those additional features that you're talking about, how simple to use can you make the API? Because what I saw on the slides, the C API, I just drove home the point again that C is a terrible language for a security policy.
Yeah.
How simple can we make the API so that people who are not interested in security policies can actually just a few simple statements, tooling does the rest, and you get a policy that is reasonable for your program?
Yes, that's a great question. So the question is, how simple can we make the API when we use Landlock wrapper libraries, and we have existing Landlock wrapper libraries in Rust and in Go, which are written by Michael and by me, and there are other ones in Haskell and in Perl, I believe, in Python. I'm not 100% sure about these because they're done by other people as well. I'm going to talk about the Go version because I know that one better. So I unfortunately don't have a slide on it, but the invocation in Go is much simpler than in C. So the way you would use it is you say landlock.version5.besteffort.restrict, and then you say read-only path such and such as an argument, and then read-only path such and such as an argument, and read-write path such and such as an argument. So if you create, overall, if you have 2 or 3 paths that you want to permit in your policy, that entire call does not take more than a few lines. It's basically one function call with a bunch of things in front. There are other APIs where this is simpler. People don't like to hear it here. I guess like OpenBSD has a similar API which is called Pledge, that is only a single C call. We can't make the API quite as simple as that because we have more backwards compatibility issues that we're looking after. We have stricter guarantees for that. So it is definitely necessary that you need to spell out as a caller at what level you want to use this the Landlock API, and which really means that you are spelling out what operations you're going to restrict. Because if we weren't spelling it out, then in a future kernel version, it would start restricting more, right? And then it would break your backwards compatibility guarantee. And so, because we don't want that, it has by necessity, it has to be a little bit more complicated. But these libraries, they can solve that best effort mode problem for you, right? They can do the downgrade to older kernel versions. In C, we currently don't have a support library that does that. Maybe we're going to create one at some point. But it's also a little bit because we try to keep the C API as simple as possible and force ourselves to make it easy enough to use also when you're using the bare syscalls. Yes?
Is there any provision to override the policy defined by the developer?
Okay, the question is whether there is a provision to override the policy that the developer did not intend no, there is no way to do that. Unless, of course, the developer puts a flag into their program that lets you do it, right? Yes?
Do we maintain a state here? Like, you would run that initialization program and you go give provisioning to specific ioctl operations, and then it died, and then a new application is running. So if it tries to change the provisioning, I mean, are you maintaining the state at what was older privileges, it got modified, or I mean, there is any kind of auditing?
So the question is whether whether we are maintaining a state in the policies. I hope I understand this question right. No, there is no state maintained. Once you establish the policy stays as it is.
Yeah, I'm saying who can override, like similarly, can anyone override it if once the initialization task has been killed? So let's say you have now new applications running. So those policies are still in place, right?
Okay, so the question is about whether the policies are still in place when the task has been killed. So the policies that you establish, they only apply to your own program. So they only apply. This does not apply globally. No, this is different to SE Linux and AppArmor in that respect. That this is, it's not top down where it's from the outside controlled what the policy is, but it is bottom up. It's the programs themselves that realize, oh, I may be doing something that is potentially dangerous, maybe using a bit too many dangerous libraries here. So I rather put another sandboxing layer around it for safety. And then when they enforce that policy, the policy applies to their own process. It applies to their child processes, but all the processes around that are not affected at all, unless you pass around the file descriptors in crazy ways, but it's unusual. Yeah. This is, by the way, also a reason why enabling Landlock should be very lightweight for distributors to do, because the processes that don't use Landlock, they're not going to have a policy, and then the only thing that the Landlock LSM does is it returns very quickly.
So is there a plan to add something like this system-wide, like application which is privileged can do all the policy setting and can be read afterwards? It can control still the policies will be intact for unsupervised applications to use.
You can use it for system-wide things as well if you want, right? For example, if you're the developer of Systemd, you could add Landlock to Systemd, and then it would still work for the services, right? You can still use it to build sandboxing tools, and as long as it's basically aligned with the Unix process tree of parent and child processes, and when you enforce your policies at a high enough level, it applies to everything that is below, and that way you can still use it for more wide-ranging policies. Yes?
Can a library introduce exceptions to Landlock policy?
That's a great question. So the question is, can a library introduce exceptions to Landlock policy? We don't currently have a mechanism for that. That's actually, you're hitting a weak point with this question, because the interaction with shared libraries is tricky, right? If you load a shared library and it gets deployed separately from the actual application, and if the shared library changes what it does, it becomes harder to say what the policy is. And there is currently no mechanism for that. I know there are people around here who have said that they're potentially going to work on this, but yeah, so far there is no real mechanism for it. You have to come up with something yourself for now. Yeah. Yes.
I think it's potentially unsafe to allow exception, because if single library gets compromised in any way, the whole idea is gone.
Yes, so the remark was that it's potentially unsafe to permit exceptions for libraries. It is potentially unsafe. It is a difficult question to figure out. Yes, absolutely. Yes.
But I think the question also goes the other way around, which is you may want to shield a library to have some kind of context, like transient context, where when you call into a library, the library should be able to say temporarily, I want to restrict what I'm doing as a library, that I only access it and these files. So in some sense, be able to stack a temporary library context on top of your policy and then unstack it, knowing that it's and that's also not possible. So it's more a problem of generic composability of the context.
Yes. So the remark was that the libraries could potentially have a policy that only applies to the library in the library context, and within the process that there is a part of the policy that only applies to the library. This is in practice difficult to do because the security boundaries that exist within the process are even more unconstrained, right? Like a library can very easily modify the memory of other pages in the same process, and then it can very easily influence what is happening elsewhere. So within the same process, we only apply one giant policy, and I don't currently see a good way to make that possible, that you can have multiple policies within the same shared user space memory. Okay, no more questions? All right, thank you very much.
SSH is pretty well locked down with Gadget, which makes it almost impossible to link into SSL to do the crypto, and we want at least to use our crypto accelerators, which are of course devices. And whenever we want to have our own SSL provider or engine to be used with OpenSSH, we have to go to SSH, ask for an exception for that very part, which is of course ugly, or to convince our distribution partners to get an extra patch. So something of a generic solution for that kind of problem would be really nice. Now, I do not know whether OpenSSH uses Landlock as their sandboxing mechanism, but if there were a sandboxing mechanism that would allow for, say, mild restrictions, and that's probably a very subjective notion, hard to grasp, that would be helpful.
Yes, yes, absolutely. And to be fair, this problem, thanks to building, this problem actually applies probably to most sandboxing mechanisms, right? It's not only Landlock that is affected by this. Right? If you go to shared memory,
define these integration.
yeah, you have to somehow make it for it.
But I like the way Sandbox does it. Landlock does it so.
The same point of view, great.
In this case, OpenSwitch has to be using that Landlock and give a provision to the whoever is the user to provision to allow that OpenSwitch still access the.
I think so. I think that the right way would be that OpenSSH has an interface for you and you can hook into it.
Provision it, yeah.
But it's, as he also said, if this becomes too generic and too really, we load this library, okay, you get what you want, you get what you want, you get what you want, and suddenly you have everything, presumably, right? So that also changes.
Yes, I know.
It's a tricky issue.
So what's the solution you guys?
Currently, we try to convince OpenSSH and now for opening, they just we have a code of IOs that
I've done it at home.
I think we asked.
I don't have a published house, but you can just
all
find it together very easily with one of these example tools. We have both in Rust and both in the kernel and in the Rust library and the Go library. We have 3 different tools that show how to use this, and they are very simple sandboxing tools that you can use to run a program.
And that's something basically somewhere else that's
the one line to say
gets
everything is read-write, and then you run a shell within it, and then everything that executes underneath is read only, and then of course you can take the time directories. For big applications, I've done it with both Approach and Monkey Island. So Monkey Island only for fun. You can basically, if the application is too big, you just put it somewhere in temps. You say this is where you get to read and write. And my home directory is no go for them.
I'm not sure
It's a big error. It's a very constraint.
And we don't have any access to change. And there is no other I mean, I'm saying something similar to this.
And use plugin mechanisms to generic crypto libraries. We want a program that uses if it wants
I promised 5 times that I have mentioned that we
I mean, we were not exactly using it, have heard of it, now it looks like it's easy to use, but yeah.
It's just a different approach, right? It complements a little bit what you can do with AppArmor and SEO.
Less towards what all we have. I mean, like, whatever I got to know from this presentation, like Landlock or SEO, they're not exporting it, but we have used
Hello, good morning. My name is Tara, and I am here to talk about Linux virtualization-based security and some of the kernel integrity features that we have enabled via LVBS. So I work at Microsoft, and my team and I have been working on this for last year and a half, 2 years now. So quick look at the agenda. So if I know some of you have attended LSS North America earlier this year, and we did have a very similar presentation there as well. So the initial few slides, which introduces what is LVBS and the basic architecture, is probably similar. And then we get into kernel integrity, particularly memory protections and module loading, and that is probably different this time. And I do have a demo, and then we conclude the presentation. So to start with, I want to touch upon the motivation behind this project. The motivation here is that Linux kernel itself, being complex, is a highly lucrative target for attackers, and we do increasingly hear about privilege escalation attacks in the kernel. And the goal here with LVBS is to harden the kernel against such attacks and to ensure that in event of such attacks, the existing protections that have been placed on the kernel cannot be turned off by the malicious attacker. And also that certain critical resources in the kernel, like keys, memory, registers, etc., remain protected in event of an attack. With that, what is LVBS? LVBS is Linux virtualization-based security. It is inspired from Windows VBS, and it uses hypervisor and hardware virtualization support to protect the guest OS. But unlike Windows VBS, here we do target and we want to have open source architecture. By that, what I mean is that, of course, we want the code to be upstream, and we do have a GitHub repo with all the code that we have developed so far and all that. But we also want this architecture itself to be hardware agnostic. So we do have this working on AMD and Intel x64 processors today. We can enable this for ARM64, though we are not working on it at this point. More importantly, we want this to be hypervisor agnostic. So we have this again working on Hyper-V and KVM, though this presentation itself will focus on Hyper-V. So a quick look at a Hyper-V based system and Hyper-V's virtual secure mode. So in the picture here, there's hardware and there's Hyper-V on top of it. And then Hyper-V divides the system into multiple partitions, one root partition or host partition and multiple guest partitions. And through VSM, what Hyper-V does is it allows for each partition to be further subdivided into separate execution environments. And these environments are known as virtual trust levels or VTLs. Theoretically, Hyper-V allows for 16 VTLs, but for purpose of this talk and for any practical purpose, we only talk about 2 VTLs, VTL 0 and VTL 1. And the other property that is established through VSM is that higher VTLs have more privilege over lower VTLs, which means in this case, VTL 1 is a more privileged execution environment than VTL 0. And some of the other VSM features include virtual processor state isolation. So virtual processors, they maintain a separate per VTL state, and each VTL can define its own set of private processor registers. It allows for memory access and hierarchy protection through extended page table or second level page tables. And each VTL does maintain its own set of page tables or guest page tables, the first level page tables. And further, a higher VTL, like in this case a VTL 1, can impose memory restrictions on lower VTLs, VTL 0, which the lower VTL cannot turn off. Finally, each VTL has its own interrupt subsystem, and each VTL has its own interrupt and intercept handling capability. This allows for every VTL to process its interrupt without interference from a lower VTL. And here is the link if you want to know more about Hyper-V and VSM. So let's relook at the goals, right? So through LVBS, again, what we want to do is to ensure that in event of a kernel attacker, we ensure kernel integrity. By that, what I mean is we ensure that kernel memory and critical registers are protected. And two is in event of a kernel attack, in the event of a kernel attack, we want to protect critical system resources like passwords and secrets, etc. And this talk primarily focuses on kernel integrity, not the second goal. So with that, here's the threat model for kernel integrity. Here, what our security goal here is to protect kernel from a user space attacker who has established privilege escalation by exploiting a kernel vulnerability. And in this case, within the TCB or trusted computing base, Hyper-V and if applicable, the host OS does fall within the TCB. What is outside of the TCB is the guest OS user space and the guest OS kernel itself after a certain level of boot. And finally, I want to say that Linux kernel itself establishes all these protections. Kernel is self-protected. And what we aim to do via LVBS is defense in depth. By that, what I mean is the protections that the kernel enforces, we want to move it up or down a level depending on your view of where hypervisor sits in the virtualization stack. Through which we want to ensure that even if the kernel gets compromised, these protections cannot be turned off or altered with. So that brings us to, this is the high-level software architecture of LVBS. So again, there is bare metal. Hyper-V runs on top of hardware. And then then this is a view of a guest partition that Hyper-V has established. So the partition is divided into two, VTL0 and VTL1. And we have a secure OS now running in VTL1. In our case, for LVBS, we do have the secure OS is a minimal Linux kernel. Why minimal Linux kernel is a discussion for another day. It's a full talk on itself, so I will not get into that here. But what runs today is minimal Linux kernel. And all those pink boxes that you see in secure Linux kernel are the bits and pieces that we have enabled or we have written code for to ensure that the secure kernel can take in requests from the guest kernel, and then enforce those requests or enforce those protections via Hyper-V. And also to make sure that it has the capability to handle exceptions in case of a protection violation. And finally, the interesting piece on the guest Linux kernel are the green boxes, which is the hypervisor agnostic layer. We call it hypervisor enforced kernel integrity layer, and we have submitted RFC patches in the mailing list. We have submitted 2 RFC patches so far, and so work is in progress to get it upstreamed. And this is the agnostic layer, so this remains the same irrespective of the hypervisor underneath. If we replace Hyper-V with KVM, this piece or these green boxes remain the same. What will change is again the pink boxes in the Linux kernel. In our case, this is a Hyper-V VSM driver, and this driver allows for the secure OS to be booted in VTL1, and 2, it collects all the protection requests from HECI or the hypervisor agnostic layer and passes it on to the secure OS. Okay, so very quick look at the boot sequence here, because this is very quick look at the boot sequence. So one of the basic assumption we have is that we need secure boot enabled. This is a security solution, so LVBS needs secure boot enabled, which again means that if secure boot is enabled, we assume that the guest kernel can be trusted till the point where the first user process starts running, which is the init process in case of Linux, because the guest kernel itself is verified by secure boot. And so till that point, we assume that the kernel probably is vulnerable, but it's not compromised yet. And after the first init process starts running, we assume that the kernel can be compromised. With this assumption, how the boot sequence for LVBS today looks is that guest kernel starts to boot, it does its initialization setup, and then it loads the VSM, Hyper-V specific VSM driver, which goes ahead and verifies the secure OS binaries, which is part of initrd. And it loads it into a previously established memory space, boots the CPUs in this boots the CPU in the secure OS. Collects all the protections from the hypervisor agnostic layer, sends it to the secure OS, and the secure OS applies these protections, and finally, there ends the boot process. And finally, the guest kernel asks the secure OS to actually lock down these protections, and there the boot sequence ends. Okay, so talking about VTL0, VTL1 interfaces, there are two kinds of interfaces. One is a synchronous interface, in which case a virtual processor enters VTL1 when it wants to enter VTL1. So it explicitly makes a hypercall. It is called a VTL call or a VMM call to enter VTL1. And in this case, we have established a bunch of opcodes for these VTL calls. And we allow for only these opcodes. So if the guest OS issues a VTL call with the opcode that we have not defined, secure OS returns an error back. And so these are the only opcodes that a VTL call supports today. And the second interface is an asynchronous interface. And there are two interfaces here. One is secure interrupt interface. In this case, a virtual processor will enter a higher VTL, in this case VTL1, if it receives an interrupt in VTL1, and the Hyper-V ensures that the VP is switched to VTL1 in this case. And the second asynchronous interface is a secure intercept interface, where if VTL0 violates VTL1 protection, the VP that triggered that protection violation is switched by the Hyper-V over to VTL1. These are the two asynchronous interfaces between VTL0 and VTL1. So with all this, let us start looking at memory protections itself. So like I said, kernel integrity here is two pieces, register protection and memory protection. We talk more on memory protection and then module loading in this talk. I do have slides on register protection, and we can get to it in the end if we have time. Okay, so for memory protection, what happens is guest kernel boots. It loads the secure OS, and after that, the hypervisor agnostic layer, the HECI layer, comes in, and it allocates and it collects permission for every guest kernel page in the every physical page in the guest kernel, and then the guest kernel issues a VTL call, which is the protect memory VTL call with all these memory ranges and permissions to secure kernel. Secure kernel, once it receives the protect memory VTL call, calls into Hyper-V, it's a hypercall, and to set these permissions in the extended page tables or second level page tables. And then the control returns back. So this is a single call, just at the end of boot sequence before the first process is called. First user space process is called. It's an immutable call. Once these permissions are established, VTL0 can no longer go and explicitly change these permissions in the EPT. And secondly, we do issue a lockdown VTL call from VTL0 to VTL1, upon which VTL1 revokes access to most of these VTL calls that establishes the protections. So this ensures that the protections we set are immutable. So with that, now once these permissions have been established, this is how the kernel memory space itself looks like. There is kernel read-only data section, which has read-only permission set in EPT. Text space, which has read and kernel execute permission set. VTL1 memory space, that gets no access from VTL0. VTL0 cannot read, write, or execute from VTL1. And then rest of the kernel memory space, which is read, write, and user execute permission. The thing to note here is that by default, without LVBS, the permissions in EPT is read, write, kernel execute, and user execute for all guest pages. Okay, and once these protections are established, if there is an EPT access violation, memory intercept is injected into VTL1, and the secure OS handles this memory intercept by raising a general protection fault in the guest OS. So this is the VTL call that we issue to actually lock down the protections. This happens at the end of establishing all the protections. We establish all the protections, and guest kernel goes ahead and sends this VTL call, which says signal end of boot to VTL1. At that point, VTL1 sets an end of boot flag and comes back. And what happens as a result of setting this flag is that all the VTL calls that are listed in the table here are revoked. And any attempt to invoke them will actually return an error back from secure OS. So let's relook at kernel memory space again. Okay, in this case, these are the kernel sections. Then there is a permission that is enforced by through LVBS in the EPTs. And then what the last two columns show a bunch of features. These are kernel features. This is not an attack or anything. These are actual kernel features. That various kernel text patching features that goes ahead and modifies these established permissions. So there is text section which has read kernel execute, and there is all these text patching features: ftrace, live patching, jump label optimization, static call optimization, kprobes, that actually tries to reset the read execute to read write execute, patch the text, and set it back to read execute. The read only data section remains read only. Similarly, data and BSS section remains read write. There is module loading reserved memory, which is set as read write during boot. And during module loading, the module loading code sets some parts of these memory to read or read execute, depending on where it loads the read only data or the module text section. Similarly, there is crash kernel reserved memory, which again is enforced with read write permission during boot, but KXer can come in and change the permission to read write execute to load and boot a crash kernel. And finally, the rest of the memory space, which is again read write, but eBPF JIT can change it depending on what we load to read execute, depending on the program we load. So this brings us to the point where we implemented till this point, and then and we had the kernel working, we had LVBS working, but none of these features working. Okay, because kernel is locked down at this point. With the VTL call that we sent before, which said signal end of boot, we lock it down, and we revoke access to any of these VTL calls, and none of these features were working. So then we started enabling these features one at a time, and we have module loading working today, and we are working on some of the other features. But the basic design principle behind enabling all these features, any of the text patching features with LVBS, is that the secure OS in VTL1 should be able to verify, authenticate the text or the blob independently. If needed, copy the text or the patch to VTL0 memory, or verify that what VTL0 has copied is valid and is not being tampered with, and then change the VTL0 memory permissions to what is needed, all in one atomic operation. VTL0 should not get involved in between these steps when VTL1 does this. So let's look at how we did, with this principle, how we enabled module loading. So one of the first things that the secure OS running in VTL1 needs for establishing independent module verification is a bunch of kernel information from VTL0. This includes the build and boot time certificates, revocation certificates, and kernel symbol table sections. So we did add a VTL call, which is called the load kernel data, through which we can load any of the VTL0 kernel data at boot. And this again happens before the kernel is locked down. And so through that, we load relevant VTL0 kernel data. In case of module loading, these are the kernel data that we need. As we add more features, and if we need more kernel data that needs to be sent from VTL0 kernel to VTL1 secure OS, we can do that. And today, secure kernel on receiving this creates a VTL0 trusted keyring and loads the VTL0 build time certificates, adds the revocation certificates and hashes to the blacklist keyring, and it copies and maintains its copy of VTL0 ksymtab. So, and that brings to module loading. So during module loading, what happens is the guest kernel or VTL0 comes in, tries to load the module, allocates independently, it verifies the module depending on whether config module, I think sig is set or not. And then it tries to assemble the module into all the sections, it applies all the relocations and all that. And after that, what we did is we added a VTL call called validate module, which passes the initial blob, initial non-modified blob, and all the memory sections that VTL0 has established for the module and some flags. What VTL1 does is that it authenticates the module using the previously established VTL0 trusted keyring, and then it reconstructs the entire module in VTL1 memory space. And it compares all the reconstructed memory sections with the memory sections that VTL0 passed. And if this matches, and only if this matches, does it issue the hypercall to change the permissions in the EPT. And once that happens, it returns back. And when it returns back, it returns a unique token back, and that is needed for the next part of module loading. So one thing that I should mention here is that because this is a Linux kernel, a minimal Linux kernel that runs in VTL1, we could actually reuse a lot of Linux's module loading facilities and functions to independently reconstruct the module in VTL1. We didn't have to actually go ahead and write a lot of that infrastructure. We could just reuse most of it that exists. Okay, so the module is loaded, but then once the module init is called, what happens is that we need to reset the permissions of the init sections because init sections do get deallocated, and also there could be data that needs to be set as read-only after init. And this happens through another VTL call, which is called free module init. And in this case, as part of this VTL call, the previous unique token is passed to VTL1. So VTL1 is able to identify which is the module with that token, and so it goes ahead and applies the relevant permissions. So in case of init sections, all it does is it changes the read execute to read write, and in case of read only, it goes and sets. In case of read only after init, it goes and sets the read write to read only, and then it returns back. So I do have to say that there is still work. We are still and it works. But we are still working on enabling some of these architecture-dependent features with module loading, and they are red booleans and some of the CFI features and return thunks and things like that. With that, I do actually have a demo that kind of shows some of these things, or attempts to show some of these features. Let's see if this plays. Okay, it doesn't. I think okay.
I'm attempting to show basic LVBS protections. For this, I have two kernel modules. The first one here is very simple, and all it does is define, fill, and expose a read only after a init buffer. The second module here tries to mimic an attacker who has gained entry into kernel. In this test, I initially read and record the value of byte 0 of earlier created read only after a init buffer. Then I spawn a thread that will change the permission of this read only after a init buffer and write into the buffer. This is possibly a very simplistic view of a kernel attack. Finally, before exiting the test, I wait for the kernel thread to finish running, and then I check the task exit code to determine whether the test passed or failed. If the thread ran to completion without any errors, The test actually failed because the attacker managed to write to a read-only buffer. On the other hand, if the write did not go through, the test passed because the attack was thwarted. First, to show status quo, I run these tests in a system without LVBS. Here, no support for Heki in the active hypervisor means I have turned off LVBS, and hypervisor enforced kernel integrity layer does not have a hypervisor attached. To begin the test, I first insert the LVBS_test_mod, the module that exposes the read-only buffer. It loads and there is no error. A quick look at dmesc shows that the module should have been signed, but kernel is not in an enforcing mode, and so it lets it load anyways. I now insert the second test module, the module that mimics the attacker. Again, this is a very simplistic view of a kernel attacker, where they have kernel access and they have gotten hold of this read-only buffer, and they can change its permissions. Looking at dmessage again, we can see that the module init ran successfully, and the thread that actually tampered with the read-only buffer also ran to completion. And hence the test itself failed because the attacker managed to write to the read-only buffer and change the value of first byte from 0xAB to 0x87. Now I run the same tests in a kernel with LVBS enabled and with secure kernel loaded in VTL1 that can enforce the memory protections. Quick look at guest kernel or VTL0 kernel dmessage shows that Heki is fully enabled and all these various protections are applied. And what you see here on the side is the console log from VTL1 secure kernel. As the initial step, I again load the first test module that establishes the read only after init buffer. And this failed. An inspection of the VTL0 dmessage and VTL1 serial console shows that, as we saw previously, the module is not signed, and even through VTL0 kernel wanted to load the module, VTL1 secure kernel refused to, and hence the module could not be loaded. Here I quickly sign this module. And now I am able to load this module and establish the read-only buffer. What I show is signature verification, even though it's not enforced in guest kernel, gets enforced by VTL1 kernel. VTL1 kernel will refuse to load the module if the module contents have been tampered with, though that is harder to demo. Now I load the already signed second module that mimics a kernel-level attacker trying to modify a read only after a init buffer. Looking at the dmessage, we see that the kernel thread attempting to tamper with the read only after a init buffer got killed, and the test itself passed, which means that the read only buffer could not be written to. Also looking at the VTL1 console, we see that a memory access violation intercept was raised, and as part of handling this intercept, we raised the general purpose fault in guest kernel. This brings us to the end of the demo.
Okay. And now to some of the lessons that we learned through this process. The first one is that text patching itself or dynamic code injection is the features are quite nuanced. Like I said, we have module loading working, and we are working on some of the other text patching features, but they are quite nuanced, and they do add non-trivial amount of complexity towards basic kernel integrity that we want to enable with LVBS. Second is that just the fact that we sat down and listed all the text patching features and looking at them was mind-boggling. It's not like we have looked at and used all these features at one point or the other. None of them are new, and I'm not saying that none of them are useful. They are all useful for various different reasons, right? And some of them are security critical, like live patching and things like that. But the idea that Linux kernel supports so many text patching features is really it's something thought-provoking. And we probably do need to at least question more features that get added which dynamically injects code into the kernel. And finally, that VTL0 and VTL1 kernel having it, first of all, the VTL1 kernel being a minimal Linux kernel helped a lot because we can reuse a lot of the functionality to verify and establish authentication for a lot of these text patching features. And having it built from the same source also allows for a lot of code reuse. So what is next for us? We do want to enable all these other text patching features that we talked about. And I do have the code uploaded into GitHub, everything that we have done so far with 6.6 kernel. And we are planning to send out the first set of patches to mailing list for review and comments and things like that. And that brings us to the end of this presentation. That was in one time.
Sorry, I have one question.
Oh, okay.
So, thanks for the talk. Can you say a little bit about how you're going to, when you institute the protections through EPT, right? Do you also track the first level paging structures in the guest?
In the guest kernel, those are the permissions that are passed from the guest kernel to the secure OS.
Right, and so the hypervisor applies the permission overlay through the EPTs.
The hypervisor establishes these permissions in EPTs. And when an access happens, hypervisor makes sure that it checks both the first level page table and the EPT.
Well, the hardware checks the first level page table.
Right, right.
But if you don't monitor the first level paging structure in the guest, you could have an alias that can change the permissions. Or like think of like two pages, let's say both are execute kernel, right?
Mm-hmm.
And they're mapped from guest virtual address 1 and guest virtual address 2. I can swizzle, again, assuming the guest attacker that has right, they can swizzle the guest virtual addresses across these two pages. And from the APT's permission perspective, they're both fine because they were both marked as execute supervisor.
Okay.
And they will still go through and it'll effectively be like a ROM.
Yes, so this doesn't provide page table protection. So that is HSLAT. That is yet to be implemented in this solution. Yes, that is something that we can extend this to. Yes. Okay, thank you.
Down for the virtual people, they won't see anything, but they'll hear you.
Yeah, sure.
And this session doesn't actually start until 12.
Oh.
So for the virtual
view in the, just raise the hand. How many of you are familiar with it? Okay, quite cool. So eBPF for networking. Yeah. eBPF for observability. Okay, nice. And for security. Okay, nice. Plenty of people know about it. Perfect then.
So it's like a logical virtual process. So think of it as like one VM being split into two VMs. So she's basically in the context of one VM she actually runs. So it's really good just this is an option.
So just before I start, the video streaming will be disabled for viewer online. This is not a bug, this is a feature. So hi everyone, my name is Francis Laniel, and today I will present you how you can use Inspector Gadget to verify and sign eBPF programs. Yeah, seems we will need a bit more time for the presentation actually. Okay, so a false start, it even occurs in the Olympic Games for athletes, so I guess it's okay if it occurs to me. So, my name is Francis Daniel, and I will show you how you can verify and sign eBPF program using Inspector Gadget. First of all, what is eBPF? According to Brendan Gregg, a kernel developer, eBPF does to Linux what JavaScript does to HTML. With eBPF, instead of a fixed kernel, you can now write many programs that run on events like disk.io, which are run in a safe virtual machine in the kernel. So let's now take a look at what we have in the kernel, which is related to eBPF. So first of all, we have the BPF syscall. It is the main entry point to the eBPF subsystem. The BPF subsystem call, it acts a bit like an ioctl. You will have plenty of flags to do different stuff. So first of all, you will want to load an eBPF program inside the kernel by using this syscall and the corresponding flag. So once you load your eBPF program in the kernel, it will be handed to the verifier. The verifier will verify the program. For example, it will ensure that there is no infinite loop, or that you do not dereference a null pointer. Once the verifier deems it safe, it will hand it to the just-in-time compiler, which will translate the eBPF bytecode to the machine code. With the BPF syscall, you are also able to create specific data structure, like which are named eBPF maps. Note that you have plenty of different types of maps. You have array, hash map, ring buffer, puff buffer, plenty of them. So, to actually write an eBPF program, you will use your favorite text editor. You will write it in a syntax which is nearly that of C. And then you will compile your eBPF program to eBPF bytecode by using the clone compiler and specifying the eBPF target. So in your eBPF object file, you will have information over your program and your maps. So let's say that in the remaining of this example, we wrote a program which traces the exact syscall and which will get the command, the name of the command, which actually was created by the exact syscall, and it will store this into a map, for example, a perfring buffer. So you will load your eBPF program inside the kernel. Nowadays, very few people use the BPF syscall directly because it is quite complex, so we rely on eBPF-related libraries like libbpf for C, Cilium eBPF for Golang, libbpf-rs for Rust, because these libraries, they offer some helpers to interact with the BPF syscall. So the first step is to load your eBPF program to the kernel, the verifier ensure everything is okay, the just-in-time compiler does its job compiling it, and so it will be installed as a hook, for example, a hook to the exact syscall. So we will also create the associated map, the perfring buffer that we want to use by using this library. Now at runtime, if I have a process, for example, bash calling ls, then it will create ls by using the exact syscall. And so the BPF program will be run because the exact syscall was triggered. It will write the information in the eBPF map, and by reading the eBPF map from user space, we will be able to get the information that the exact syscall was actually invoked to create the ls process. So eBPF seems quite appealing and quite cool, but it has some problems. So first of all, with eBPF, you have some helpers. So these are some functions that you can call from the eBPF context and which will act on the kernel or maybe give you some information over the kernel. So for example, if you want to get the current task, then there is an helper to do that and plenty of other helpers. So some of them can be used in a bad way. The first one, the BPF override return, which, as the name suggests, override the return value of the function that it is actually traced. So with this, for example, you can return an error code as the return value of the exact syscall. So this helper can really be used in a bad way. So hopefully it needs a specific kernel option, config bpf kprobe override, which is not set in distribution kernel. You only set this for test purpose only. The second one is the BPF send signal, which can be used to send signal to other processes on the machine. So with this, from the eBPF context, you can actually kill another application by sending either sigstop or sigkill. Moreover, despite the fact that eBPF programs are verified and deemed safe, the verifier itself is not flawless. It was the subject to some CV around last year, and particularly the last one, CV 2023-2163, was only fixed at the end of 2023 in 6.3 kernel. So the impact in BPF component by this CV was the path pruning. So the verifier will also do for you some optimization. So for example, if you have an if false, the verifier will be smart enough to know that this path will never be taken, and so we will remove all the eBPF bytecode associated to this path. And so this path pruning function was actually abused to get a root shell in by using this CV. So I propose you that we take a look at a short recorded demonstration of this CV. So the CV was actually found by people from Google, and so the exploit was also written by them, and I only used the exploit. I did not write it myself. So I run it in a virtual machine using the 6.2 kernel, so a kernel which does not have the patch. And so as you can see, we get a root shell inside the virtual machine. So yeah, this CV can actually be used in a bad way. So now my presentation is about Inspector Gadget, and as a maintainer of it, I should describe it a bit. So as stated in our project documentation, Inspector Gadget is a set of tools and framework for data collection and system inspection on Kubernetes cluster and Linux host using eBPF. So with Inspector Gadget, you have a set of tools that we wrote and that we'll call the official gadget, but you can also write your own gadget, and this is really useful for you and for the remaining of the presentation. So Inspector Gadget targets two different contexts: Kubernetes cluster with the IG Kubernetes binary, and the Linux host with the IG run. Note that IG can also be used as a daemon in this particular context. For Kubernetes context, we deploy it by using daemon set, so you have one pod for each node of your cluster, and inside this pod we have the gadget container running the IG Kubernetes binary. To interact with all this binary, we have the kubectl gadget to interact with the IG Kubernetes side. Note that you can also use headlamp, which is a Kubernetes UI, and you can also write your own client because the communication uses gRPC here. And to interact with IG when run as a daemon, we have the gadget-ctl binary. So Inspector Gadget does plenty of things for you, and one major thing that it does is what we call enrichment. By doing enrichment, we will map low-level information. For example, an exec syscall was done with higher-level information, in which Kubernetes namespace this syscall was done, by which container was it done, and all this sort of thing. Note that by using what we call operators, you will be able to sort, filter, and format the information that you get from eBPF. In the remaining of this presentation, I would like to focus on the OCI operator, because this is the one that we use to package the eBPF program in Inspector Gadget. So in Inspector Gadget, we name our tool Gadget, and a gadget is simply an OCI image containing different elements. The first, and really important, are the eBPF program. Note that you can have one or many. For plenty of our gadget, we have generally two eBPF programs, one for AMD64 architecture, the other for ARM64 architecture. You can also add some WASM modules if you want to do specific enrichment. There is also some metadata in the YAML format, which will give you some information about the gadget itself and can also be used to write help information with regard to how to use this gadget. And you can also add some BTF-gen information, which will be really useful if your kernel lacks BTF information. Then you will be able to use this gadget here. So by using OCI image, we have two big advantages. The first one is that we can share the gadget like container image with user experience, which is almost that of Docker. You can push and pull image, you can run them, and we can also sign them like container image, and this is really important. So to sign them, we rely on cosign, and we do this in our CI for each commit on main, for all our release. And it is quite simple as using cosign in the CI by using the sign subcommand, by giving the private key we want to use to sign, giving --yes because we're running in the CI, so we do not have, we will not be prompted. And by using the --recursive, we will be able to sign the whole image in case of, for example, we have different layers, for example, one for AMD64, the other for ARM64. So note that in the case of our official gadget, they are signed with our official private key, and we give also somewhere, which is easily available, the corresponding public key. So by doing so, it has two side effects. The first one is that it will push a signature, and the second is that it will push a payload to the container repository where your image, where your gadget lives. So let's take a look in practice of how we do the verifying of a gadget by leveraging the cosign and ORAS API. So let's say, for example, I have the Inspector Gadget repository, then I have my developer laptop. I want to run, let's say, the traceexec gadget. So I will run it with the AG run traceexec, specifying the digest of the gadget I want to run. It will pull the gadget locally in my developer laptop. Then, by using the digest, we will get also the corresponding signature. Inside the signature, which is simply a JSON object, we will have different information. So we will have the digest of the payload. And then we will also have the signature, which was actually generated during the signature process. So thanks to the digest contained in the signature, we will get the payload. And then we will feed some information in what we call a verification process. So the verification process will take as input the public key, which corresponds to the private key used to sign the gadget, the actual signature, and the payload itself. If the gadget was signed by using the private key corresponding to the public key, everything is okay and the execution can continue, otherwise execution will be denied. Note that for developer purpose, we have a flag to disable this behavior, but use it at your own risk. After we've verified, we need to do one extra step, is to ensure that what we verified corresponds to what we signed. So we take a look at the payload, which is also a JSON object, and in the payload, we should have the exact same digest as that of the gadget. Let's now say that you wrote your own gadget, you push it to your repository, and you sign it too. So let's try to run your gadget. So to run your gadget and to pass the verification process, you will need to give your public key by using the -- public key flag. So note that this flag can take several public keys, so you can give your public key as well as the official one. And so since your gadget was signed with your private key and that you give your public key, everything is okay and the execution will be allowed. Let's now take a look at a case where you want to run a gadget which was not signed. So there is no signature and no payload in this repository. This time, the verification process will fail because it is lacking the signature bytes and the run will be denied. So let's now take a look at how it is done in Kubernetes context. Because in Kubernetes context, you cannot give the public key at runtime. Otherwise, it means that everyone can give the public key at runtime, and so this would not be really secure. So the public key in this context, they are set once at deploy time. So the first step is to deploy the inspector gadget to your Kubernetes cluster. So by deploying the daemon set, then a pod, then a container. And so we have the inspector gadget container running in your Kubernetes cluster. And so we actually give at deploying time 2 public keys, so the official one and yours, because you want to run some of your gadget. And so the inspector gadget container will have the information over these 2 public keys so that it can use both during the verification process. Now let's say we want to run the trace exec, the official one, then the trace exec will be verified, execution will be allowed because inspector gadget was able to pass the verification process using the corresponding public key. And now we want to use your gadget, so let's say that you modify the trace open to add information about the type of the file system where the open is done. And so here, the execution will also be allowed because inspector gadget has the knowledge about your public key. So as a conclusion, you can store eBPF program in OCA image. They can easily be signed using cosign. As you can see, just a matter of adding one call in your CI. And then inspector gadget will, in this case, verify them by leverage the cosign and ORAS API. So as a future work on inspector gadget side, we would like to add an air gap mode. So instead of deploying first the gadget container in Kubernetes context and then pulling the gadget that we want to run, we would like to deploy first the gadget with first the gadget container with some already packaged gadget, and so this would avoid us to do the pull each time we want to run a gadget. So if you are curious about Inspector Gadget and want to know more about it, of course you can ask me a question and it will be a pleasure for me to answer them. But you can also find us on our website, so inspectorgadget.io. All the development with regard to Inspector Gadget occurs on GitHub, so github.com/inspectorgadget/inspectorgadget. So if you found a problem by using it, and for example, you want to open an issue, they are welcome, you want to review a bit of code, or there is something which isn't clear in the documentation, every contribution are really welcome, and it will be a pleasure for me to review them and to take a look at them and to give you some advice on how to contribute to Inspector Gadget. And of course, we are active on the Kubernetes Slack in the Inspector Gadget channel. So it's the end of my presentation, and if you have a question, it will be a real pleasure for me to answer them. Yeah.
First of all, thank you very much for the presentation. I might be mistaken, but as far as I remember, there was an issue with dynamically generated eBPF programs. Basically, by using something like LVBS, I believe, you were able to use the library from C, C++ to basically dynamically generate eBPF programs, compile them, and then use them as a solution. I assume this is still an issue. Maybe, I mean, question to you, would it make sense to include such programs into this framework such that the programs themselves are transmitted or deployed in a very similar way to OCI images, for example, such that you sign entire programs that again generate programs which depend on the library. I guess there is the next issue. What are your thoughts on that?
So basically, you are saying that with eBPF, you are able to write at runtime eBPF bytecode by using some instruction, which is the case. And so you are wondering if the signing here will cover it, right? So sadly, no. And so the only thing that we ensure here is that it's like, for example, I send you a package. You know, I go to the post office, I send you a package. Then the only thing that this process ensures is that the package was not tampered during the delivery. Once you deliver it, if, for example, the package was for someone from your family, and you take it, and then you decided to modify it and then give it to this person in your family, then this process would not cover it. So everything which occurs on the developer laptop, sadly, we cannot do more about it as now. So yeah, this thing is only for the delivery of the OCI image. But yeah, definitely, I mean, here the thing that that we do in Inspector Gadget is that we want to be a framework for eBPF programs. And so eBPF is really low level. Some people are a bit afraid of using it. And so we need to give a bit of a safe net. To say that, okay, this is what we can offer to you. But yeah, Inspector Gadget, sadly, we need to use the capsysadmin when we deploy it in the Kubernetes cluster. And so I tried to harden everything and to reduce the attack surface as much as possible, but I'm tied with capsysadmin to interact with some fanotify stuff to do the enrichment. So yeah, sadly it's a bit problematic here. So one thing maybe that I need to think more about finding a way. I know that there are some. I know that at one moment there was some project or maybe some thinking to do something in the kernel with regard to eBPF program themselves, you know, with regard to signing. Like for example, what we have with modules. You can restrict the kernel to only load signed modules. And so this is really a good thing. And I would really like to see something like this in the kernel. And if something like this exists in the kernel, I would definitely I would definitely jump on it to take a look at it and then to code it in Inspector Gadget, because yeah, this is really important.
Makes sense. I believe this was the original intention to basically use or verify signed eBPF programs from inside the kernel, which makes sense. The problem is, again, if you dynamically create them, then you simply lose the capability of signing.
Yeah, definitely, yeah. But nowadays, you know, with using Cori and everything with regard to BTF, I'm not sure that there is still a real use case of dynamically creating it, you know, at runtime. So the only use case I can think about is Insidium eBPF. They are actually doing that for their test. So instead of, you know, having a binary in their repository, they generate the eBPF program at runtime, and so then they are able to test it. But yeah, other than that, yeah, out of the blue, I need to think more about it, but out of the blue, I do not see really a great use case where you would definitely have to do that. You're welcome. So. Yeah.
That came in my mind.
Yeah, no worries.
Hi everyone, my name is Tan Yue, and this is Fan Shiqi. We are graduate students from Landlock University. There was supposed to be a third speaker, but he's not coming because of the bad weather. So our presentation will be missing some content and will be shorter than expected. It's our first time to work on Kernel and our first time to speak. I'm pretty nervous. First, Shiqi will give you some background information about our work.
Okay, as we all know, the kernel offers over 400 different system calls, but most programs only use a small subset of them. Attackers can exploit certain system calls to launch attacks. That's why we have Systemd, which allows us to limit the system calls that a program can use. Systemd is a feature in the Linux kernel that provides an extra layer of security. It works by allowing a process to define a filter, specifying which system calls are permitted and which are not. When a process is running under a Systemd filter, any attempt to make a disload system calls will result in the process being unsuccessful. So this can help to mitigate the impact of security vulnerabilities as well as reduce the attack surface for potential exploits. However, using Systemd is not entirely secure. In the real world, the implementation of Systemd may have vulnerabilities that can be bypassed. Additionally, misconfiguration of Systemd is quite common in the production environment. Okay, next are some examples of CVEs related to Systemd. Look at this one. It allows local users to bypass intended access restrictions via crafted syscalls. So this vulnerability dates back to 2009, which is quite old, but it still demonstrates that the kernel's implementation is not necessarily flawless. Okay, the next one, it is a flaw in the Systemd policies that allow the use of ptrace. It would lead to local escalation of privilege with no additional execution privilege needed. So it has a score as high as 7.8, which is really dangerous. Similarly, it highlights issues in the implementation of Systemd. So there are dozens of CVEs related to Systemd, most of which are due to the flaws in the Systemd's implementation. So is there a better solution to reduce the system's attack surface?
Here's an idea. If we could remove system calls from the kernel during compile time, attackers wouldn't be able to exploit something that doesn't exist. Systemd can be bypassed, but this one is impossible to bypass. We propose that system call elimination, DSE. We can say usage is similar to Systemd. We just record the system call that the program will use and configure it when we compile kernel. Then the linker will remove all the code related to the unused system call while ensuring the rest of the kernel continues to work normally. Next, I will explain how this feature is carried out. We need to make modifications to kernel, and we will rely on the data code elimination to accomplish this task. First, we have to make some modification to the system call table. This part is quite simple. Once we have the list of the permitted system call, we can use set to commit out the unused system call entries. Then we will rely on data code elimination to carry out the next steps. Here's an example of how a data code elimination works. The program intern is the main function, and the main function called function A. Linker will scan the dependency tree that which function are used and which doesn't. The unused function B will be removed from the binary. These features have been used in kernel for many years, and we will rely on it to remove unused system calls and its related code. Ideally, once we remove a system call from the system call table, its associated code should be removed as well. However, in practice, these codes cannot be removed, and this is a very interesting issue. So, how did this happen? I will explain in detail the garbage collection process of data code elimination, and how the linker determines whether a section should be removed or not. There is a special assembler directive, push section. It will produce a new ELF section without any dependency information. Every time this miracle expands, it will produce a new ioctl section. So linker will remove them when performing data code elimination. So developers have to forcibly keep the sections with the keep with this one. With this keep. Only this way the kernel can function normally. So this is where the problem arises. All its table entries are forcibly retained, which results in some ioctl entries that will never be used being kept as well. The ioctl also references variables in getUser function. You can see the green arrow. Instruction and fetch sub causing getUser function to be also be forcibly retained. Their dependencies are completely messed up. So here's the thing. Keep have side effect causing our DSE to be unable to remove some code. So there's no more keep. To solve this issue and to prevent such things happen, we come up with a solution. We rewrite the push section miracle to make it have correct dependencies. You can see the yellow O flag here. This magic flag can do this job. So with the correct dependencies, we don't need keep anymore. We believe this is a more elegant solution than using keep. All places using keep can be rewritten this way. I'm not saying that our DSE is better than Systemd in all cases. It has obvious drawbacks. All programs are subject to system call. All programs are subject to system call restrictions, which is unacceptable in certain environments.
Our approach is well suited for embedded device or certain simple purpose systems. Since the programs running on embedded devices are fixed, there are no need to adjust the list of blocked system calls. Compared to CComp, DIC also doesn't require BPF to filter system calls, which offers some performance benefits. By removing code related to certain system calls, it also saves 7% of kernel image size, which is valuable for embedded device. The first version of the patch set received positive feedback from the maintainer. We are still preparing the second version of the patch set. If you are interested, you can reply our patch set in the kernel mail list. That's all. Any questions?
I'm supposed to speak into this, or is okay? Okay. Apparently, I'm supposed to start a little bit early, and hence I'm going to do this. So it's good to start a little bit early, though, because I actually have a lot of material. Yeah, I'm going to talk about Systemd TPM 2, and this is supposed to be kind of a continuation of a talk that I did at the Linux Security Summit in Vancouver last year. So those of you who have seen that one, that's good, but I have no illusions, most of you probably won't. So I'll start up with a little bit of a summary of what I was talking about then, because this is supposed to be like the update of things that happened since then. So, yeah, what's new since basically May 2023? First, to start out, what's the goals with all the TPM stuff we're doing in Systemd? This is primarily to catch up with what the other OSs provide, right? Like Windows, Mac OS, Android, all these operating systems, Chrome OS have TPM or some other form of TE support. And Linux, at least generic Linux distributions, generally does not. And I'd like to change that. So one of the key goals there is to have measured boot by default, something that Windows has been doing since, I don't know, 15 years or something. So that we can actually lock disk encryption to it and take benefit of the security properties this provides us with. It's not just about that, though. It's also about remote attestation. I think whenever you have a distributed system, right, like you look at more than one system, actually even if you look at one, just a single system as well, but in particular if you look at many systems, remote attestation should matter to you, and remote attestation should be something that actually works and not something that people have to think about so much. And the key of that is, of course, that we measure a lot of stuff that's going on in the system so that we can actually validate it externally and to see if everything's in order. So much about the goals of what we want to do in Systemd and what we are doing. So this slide and the next one is supposed to give you a little summary of what I actually talked about last year and what was the status quo back then. It's mostly for those who don't know exactly how far we are with Systemd. So that's a brief overview of the components of Systemd that have anything to do with TPM. First of all, there's Systemd crypt setup. It's ultimately, it's a wrapper around libcrypt setup, but it's for unlocking encrypted disks. But what it actually brings to the table is TPM support, PKCS11 support, and FIDO support, and a couple of other things. So it's about integration, really, right? Like the raw crypt setup tools provided by libcrypt setup maintainers is mostly just about simple unlocking with a password. This stuff is supposed to then add all the stuff on top that provides TPM unlocking and a couple of other things. There's Systemd crypt and roll. It's kind of the other side of disk encryption, which basically means it allows you to lock a disk to a local TPM. Systemd crypt and roll is what you run once to set up the disk, and then crypt setup is what you run every boot to unlock the disk. Systemd PCR extend is a tool that does measurements, like these PCR extensions. I'm not gonna say what that is again. I hope you do all know what that is. So that we can actually define nice security policies with the TPM. We need those measurements that actually reflect system state, and we need them to be done at the right time, like early enough or late enough, so that we can, like, they actually bring us value. Systemd PCR extend measures file system identity, for example, like the UIDs and labels of file systems that are relevant to the system, like the root file system and things like that. Machine identity, that's etc machine ID, for example. Then boot phases, which is actually fundamental because in many of the TPM policies you want to say that certain unlock keys can only be unlocked during the initRD phase of the system. And hence, it is essential that the TPM is basically informed of the phase that the system is currently in, right? Like, it just entered the initRD, it just left the initRD, and a couple of other ones, or it's currently shutting down, or it's fully booted up, and things like that. There's Systemd stub. Systemd stub is an EFI program, right? Not a Linux program, but an EFI program that is supposed to be glued in front of UKIs and measures the kernel components that it is booting into. UKIs, I hope. Has anyone not heard what UKIs are? Okay, there's exactly one person. UKI is a unified, 2 persons. Unified kernel images. It's like kind of what we try to push people towards using. It's basically you take a kernel image, you take an initRD, you glue it together, put Systemd stub in front, which is in our EFI stub, and then you can sign the whole thing as a secuboot EFI binary. This is fundamentally different from how classic Linux distributions do it, because in the classic Linux distributions, you load the kernel, and you load the initRD separately, and the kernel might be signed by secuboot, but the initRD generally is not. And this current model is awful, right? Like, because the initRD has no security whatsoever. UKIs are supposed to be our solution to this. As mentioned, Systemd stub is like this component that runs in EFI mode as first thing when UKI is started. It does a couple of things, and among them is measuring the components of the kernel that is about to start, and actually the ones that it is about to start, right? Like, because we actually support multi-profile UKIs now, but I'll talk about that later. Systemd measure is a tool that will predict the measurements that Systemd stub will make for a given UKI. This is you can then use these predictions and sign them cryptographically, and then have TPM objects locked to the signing key, basically. So what this basically gives you is the ability to encrypt a disk and declare that it shall only be decryptable when a specific like vendor's UKI is booted, right? Like, so you can basically say this disk shall only be decryptable on Fedora, but if you use Ubuntu to trying to decrypt it, it's not going to work. So Systemd measure is basically this tool that the OS vendor uses to after they build a UKI to predict what the measurements are and generate a signature so that the signature can be shipped along with that kernel. The last 2 things, one tool is called UKFI, or we haven't really agreed on how to pronounce that thing, but it's actually a Python script that just combines, like, does the actual combination of the different individual components of a UKI, does all the measurement prediction stuff, does secuboot signing, and yeah, it's the way how you basically take all the separate parts and turn them into like the most locked down thing you want into a unified kernel binary that you can then install. And the last thing is Systemd report. It's actually a dynamic partitioner. Now you might wonder, what does it have to do with TPMs? The thing that it has to do with TPMs is that it's supposed to run at early boot and add petitions or set up petitions. And one thing in particular it can do there for you is that it can create a petition and automatically encrypt it. Against there's a T missing, against the TPM, and hence with a key that stays inherently local to the system. The intended model for this is basically that, you deploy a /user tree of the operating system, and that's it, and then you boot for the first time, and this creates a root file system that is freshly created on first boot, encrypted at first boot, locked to a key that is specific to that system and stored in the TPM, and then you get the right semantics, which is fundamentally better, like, for example, that many other OSs currently do, which is sometimes that they ship a pre-built root file system that is encrypted against a vendor key, and then on first boot is entirely re-encrypted, right? Like, because that behavior is of course awful, because it means you touch every sector and waste a shitload of I/O and a shitload of CPU on re-encrypting everything. And this model that we kind of try to push forward, instead we say basically you separate out the stuff that the vendors provides and you monopolize that in /user, and then the root directory you can generate and have inherently local, which is a much nicer property, I think. Okay, so much about the status quo ante, and this is basically what I talked about in the last talk. So, at this point, any questions? Otherwise, we'll start with the new stuff. Okay, no questions. Okay, this is where the actual part of the talk starts, now that you're all up to speed. So what's new? There's another component that we added. It's called Systemd PCR lock. So in the stuff that I was talking about earlier, I mentioned very vaguely that we do support TPM unlocking with script setup. What that actually really means is that you can lock it to a TPM against static PCR values and against the signature scheme that I was mentioning earlier, right? Like where you have expected PCR measurements of a UKI and you can sign those, and then you can lock against that so that you can only basically unlock it if on a Fedora kernel or something like this. But these two policies, and there's one more policies addition, which is, by the way, that you can specify a PIN that we also include in the locking logic. But these things that I was just covering are limited, right? Like because they do not provide any kind of protection against modification of firmware and all these other things. Windows provides them that, and we should too. So our answer to that is the new component Systemd TPM that we added in the meantime. So what this does actually, it manages dynamic, locally managed PCR policies that take into account the inherently local components of the system, right? Like the OS vendor has very clear control of the UKIs it deploys on the user systems, but the OS vendor has no control of the firmware versions, of the extension cards, of everything else that gets measured during early boot, right? So Systemd TPM is supposed to cover all these things, all the local ones that are hard for the OS vendor to predict and hence impossible to create signatures for ahead of time. So this tool basically runs locally on every system, or is supposed to run locally on every system. It looks at the measurements that the firmware made, at the measurements that user space made and everything else made in the system, and then tries to distill a access policy from that and stores that in a TPM NV index. I hope you guys are a little bit, or gals are a little bit up to date on what TPM actually provide you with. One of these things is NV index. It's like a little bit of memory, of non-volatile memory that you can allocate on a TPM. It's very small, right? Like it's usually, you're supposed to put a key in there or a hash value or something like this, but none more. And it's referenced by an index number. So these NV indexes, they can be used to store policies on a TPM, and that you can then use to lock down other objects, right? Where you basically can say, I want to have an encrypted key that can only be unlocked if that specific NV index contains that value. So this is inherently different from what I was talking about earlier, because earlier it was all about signed PCRs, PCR policies that the OS vendor prepares. These ones are locally generated policies that are specific to the individual system. Yeah, I'm saying basically the same thing again here. Systemd TPM can cover inherently local boot components, firmware system, extension cards, also local configuration. Like for example, in some cases it makes sense to lock down the OS so that when, I don't know, BIOS setup changes are made, it refuses to boot, if that's the kind of policy you want to have. Disk encryption policies can now make use of the combination of both of this, right? Like so that you say, I want this disk to be decryptable only if the system, like if the vendor policy can be fulfilled, but also if my locally managed policy has also to be fulfilled. And if one of them cannot be fulfilled, then the system will not be able to decrypt the disk. Implementing the last bit here, right, like the combination of the two policies was actually really hard. I don't know, for the people who actually know TPMs better, the primitives to implement this are policy authorized and V and policy authorized. I really couldn't figure out to combine them. I got help from a lot of people who actually, like from the TCG, who couldn't help me on this either. But eventually you find a nice way via key sharding, basically. We lock the disk against like two keys basically, and one of them we protect with the one policy and the other one with the other. It was actually kind of like, it's a very simple solution to something I wasted so much thinking about. But anyway, that problem is solved right now, and I think that brings us into a really good position, because we at least to my knowledge, I think we now have a better support for TPM policies than Windows, for example, has, because yeah, we can lock both to the OS vendor identity keys and to the local stuff. And one of the big benefits of what we're doing here is that these policies are managed inside of that NV index, because that, like on Windows, for example, with BitLocker, which they do similar things, but they instead of changing the policies and storing them in an NV index, they keep rewriting the BitLocker superblock and put the new data there. I think our model is much, much nicer, because it basically means that we can, with one change, update the policies on any number of encrypted disks and other objects, as opposed to how BitLocker does that, because then they actually would have to go through all the superblocks and change them all. So this luxury we have because, yeah, we start doing everything 10 years after Windows did it. And what Windows, like the TPM, simply didn't have the functionality back then. And we have the luxury to say that we simply don't support 10-year-old TPMs that never have seen a firmware upgrade. Systemd PCR log. As mentioned, it's supposed to be this thing that analyzes the measurement logs and generates a policy from this. To be able to do this, it needs to recognize in the PCR logs the various components that affect the boot, right? Like it needs to be able to recognize, like, this is the firmware. This is, I don't know, the measurement that covers the firmware setup. This is the bootloader. This is shim. This is the UKI. This is the user space managed things, and like component, and so on and so on. So it needs to look at these event logs and needs then to be able to recognize each of the measurements, what they actually are about. And that is a non-trivial thing, and in particular it requires a database of things to recognize in there. So like it basically needs a database of golden measurements of components that is kept locally and that it can then match up from. This is kept very extensible in Systemd PCR log. Basically there's a drop-in directory where all components involved in the boot, right, firmware, as well as bootloaders, as well as shim, as well as UKIs, as well as user space components, can basically drop in a tiny JSON file that says, if this component is booted, expect these measurements in those PCR values. And then for each of these components, there can be multiple alternatives be defined, right? Like, because you generally want to support multiple kernel versions or multiple bootloader versions or multiple shim versions or multiple configuration versions at the same time. So you can put alternatives in these directories, and then Systemd PCR logs will try to match it all up, then tries to figure out if it recognized everything on the current boot in these in the event log. And if it did so, there's a good chance that if it now generates a policy out of that, that it will also apply on the next boot, where the changes in the measurements are hopefully going to be minimal and covered by these alternatives that we listed. One nice thing, by the way, that Systemd PCR log also provides is protection against rollbacks. This actually matters because like Windows, for example, doesn't really have that, right? Like if you just use an older version of the software or of the disk, can you still unlock it? Because we update because we write the policy into the TPM and store it there as opposed to the superblock, these things go away, right? Like because after we updated the policy, the old policy is automatically and necessarily invalidated. Nobody can use it anymore because it's not stored in the NV index anymore. Our new one is. This is something like, I put this here on the slide, might be surprising simply because on the slides from my last talk, this was like at the end, I had a list of problems that I saw in this entire endeavor that were unfixed, and I couldn't answer that question, how do we protect us against these rollbacks? This is my answer, that we figure that out. Second thing that, any questions to PCR log before I continue to the second thing that happened since then? Interesting. So the question was regarding how do I protect the data about the reference measurements. It's an interesting question because I actually got the same question yesterday and I didn't expect it then either. But the idea basically is that this drop-in directory, it exists in /var and exists in the second version in /user, and we always combine both of them. my suggestion, my assumption is that this is protected like any other resource that either comes from the OS or is inherently local. Like for example, a bootloader comes from the OS vendor, right? So my assumption would be that these gold measurements are placed in the RPM or DEP or in the immutable image that the vendor ships, right? Under the assumption that the vendor hopefully has some kind of protection for that. Like for immutable images, that means DM verity, for example, right? Like so that the same way as the bootloader is protected, or like the component is protected if it's in /user, it should also be the gold measurement that's shipped along with it is protected. In case of measurements of local stuff, right? Like for example, let's say I want to lock down the local BIOS configuration, right? Like so that I can't change, I don't know, the disk it boots from. If I lock down that part, that is of course inherently local, right? Like I can only see what the current configuration is, take a hash of it, store it away. This is going to be stored in var, right? Like because it's not under vendor control. This is under my local, like whatever the hell I decided to configure in the firmware. But my assumption is of course that /var is protected by decrypt connected to a LUX and everything like that. So my answer to your question is basically, I do not protect this particularly. I assume that it is stored in places that have inherently protection anyway, because you really should. And that's like, I'm building here basically a system to make sure that you can protect your whole system very, very tightly. And hence, because this is just a resource like any other in many ways, it's fine. Oh, and by the way, these gold measurements, like for firmware and things like that, this might be important to mention actually. You know, for firmware, we have this problem that firmwares are developed by firmware manufacturers, right, like mainboard manufacturers. So we don't have these gold measurements for them. To attack this problem, I have two strategies. Like the first one is change that fact. And get the firmware developers to eventually provide this for us, because there has been prior art. You probably have heard of FW Update D, which is like this project that maintains a huge database of mainboard firmwares and then automatically can upload them. Most of the relevant, I don't know, laptop manufacturers all play ball and provide their firmwares that way. And they already do carry, for PCR 0 as the one exception, some of the the more quality manufacturers do provide among the data that is shipped with FWUpd actually the expected measurements of PCR 0, the expected value once the system is booted up for PCR 0. That's a much, I want more, right? I don't care so much about the PCR value at the end. I care a lot more about the individual measurements. Because that gives us more flexibility with alternatives and things like this. But I think that basically means that we have a foot in the door, right? Like they were willing to give us that, so I think they can give us more. And I started the conversations with Richard Hughes, with the guy who maintains FWD, to get there. However, I have no illusions it's not something that actually is going to be universally available. For those cases where it isn't available, we do the best thing we can do, which basically means if we expect a firmware upgrade to take place, you can basically tell PCR log, please remove this component from your measurements, from your policies. Then you generate a new policy reboot. At that moment, you have all the other protections, but you loosen the protection on the firmware. And then there's an automatic logic in there that on every boot, we lock down the policy again if it happens to not be locked down again. This is kind of similar to what Windows does, actually, right? Like if we do a firmware upgrade on Windows, it turns off all the protections regarding TPM. It's terrible, but it's how it is. And I think, at least on quality hardware, we can get better if we get the FWUpd hookup, which I hope we do. And for the others, we at least don't make it worse. Yeah. Okay, so any other questions regarding PCR? That's another one.
So you mentioned that the key is stored in NVMX, right? That NVM non-volatile memory. So what's the process of protecting that key? What's the protection against accessing?
So the keys are not stored in non-volatile memory. It's the policy that we store there. And the policy is like this TPM idea it's basically a hash of a couple of expressions that says this key may only be accessed if this and this and this takes place. Like the most relevant part of this is like if a PCR has a certain value, right? Like so they serialize that into a buffer that policy and then take a hash, and that's what we store in the NV index, right? This stuff, like the TPM hardware, like if you have a discrete TPM, it's supposed to make sure that this cannot be modified, right? Like that's kind of the point of having a discrete TPM, and it's kind of the point that TPM vendors are proud about, that they make it so hard to actually modify that. I can't tell you how good that actually is, but that's the idea, right? So we do not store the keys on the TPM. What we do is we have a encrypted like for the disk encryption stuff, we take the literal keys, we give it to the TPM, it encrypts it for us with some key it has, and we store away that resulting key. So this is how TPMs work after all. Like they basically have one seed key that they derive everything else off, and we can give them stuff so that they encrypt it and decrypt it. The only things that are stored from our perspective on that TPM are that seed key, which we don't manually manage, that TPM does it on its own, and is this NV index thingy that stores our policy, if that kind of is an answer. Okay, next thing. Doing measurements is one thing, right? Like, the measurements is just this weird thing where we write it to a register, and what actually happens is it takes a hash of the old value plus the data that you're now measuring and replaces the old value with the result after hashing the result. That's one thing, right? Like, but to be actually useful, you also need to know some meta information. What was that stuff that actually got measured there, right? Like, because otherwise it's just hashes of stuff you don't know what it is. So the firmware provides a measurement log hands, right? Like it's basically just some system RAM where the firmware, whenever actually it asks the TPM to make an extension, like to measure something, it also writes a little bit of binary data that describing what it did there. It's actually a terrible buffer, and they originally added this mostly for debugging, and it's a bit problematic because it stores a lot of metadata there that isn't actually covered by the hash that they extend. Right, so that makes it questionable to use for measurement analysis because, ideally the PCR is supposed to protect this data, except that some fields are not protected. But anyway, one can work with this. So now that Systemd also does a couple of measurements of certain things that happen on the system, like as I mentioned, the machine ID and file system IDs and things like this, it's kind of crucial that we also could keep a log about this. So current Systemd versions now implement a TPM log, which is basically a JSON file somewhere in /run, and whenever we measure something in user space, we just append a little JSON objects to that. It implements mostly, but not really, the JSON TCGCL specification. That's a specification by the TPM people. The reason why it doesn't implement it 100% is simply because I think that specification is not that good. Because for example, it has record numbers in them. And that basically means that whenever you append an entry, you actually would have to read the whole file to get the highest record numbers and increase that by 1 and append the thing to the end. That makes it inherently inefficient to make extensions, right? Like, because it might work at boot, right? Like, because you expect, 100 measurements during boot. That's fine, but if we want to go for remote attestation, we also expect that there are further measurements made during the entire runtime of the system. And if every time we would make a measurement, we would have to go through the whole thing and calculate, like figure out what's the newest record number to generate, then that's terrible, and particularly as it's completely useless information, right? Like, yeah, you can count this yourself when you read it. So we drop all this stuff, but otherwise we've implemented a spec. So in other words, it's trivial to take the actual JSON data that we store there and converts them into standards conforming CL by basically numbering every entry yourself. This new policy logic is measurement log is actually what Systemd PCR log uses to make its to figure out what the policies that it shall generate. So it's actually key to that. If you now take the firmware log and our log together, you have a pretty good description of what actually happened at boot and during runtime on the system. before I go to the next slide, any questions regarding the log stuff? Question?
How does it align to the kernel's IMA? Is there any compatibility? Can you trade a mapping between that log and the IMA log?
Okay, so the question was regarding how that relates to the IMA logs. My answer is it doesn't. So basically, like, I don't know, let's just say I'm not a fan of IMA. I think it measures the wrong things and things like that. So I think talking to the TPM directly and not involving IMA is more interesting for at least my use cases. If you want interestingly, the CEL spec actually covers IMA, right? Like it's actually in there how to serialize that. If you so well, if you take the firmware logs, the UFI logs, and our logs, and then also the IMA logs, then you actually have the really comprehensive set of logs. But for now, we just ignore the PCR of the IMA because, you know, it's a constant series of measurements being made there. And I don't know, like the thing is like because the way I understand IMA, it's kind of focused towards measuring files. Right, like really fine-grained stuff. They have a high frequency of measurements, and they, on the other hand, do not have rotation and things like that. So this is something that it doesn't compile in my, like, either you decide you don't want rotation, but then you cannot measure the whole world all the time. So I don't know how, like, yeah, I understand this is a problem that IMA people are trying to solve, but yeah. So if you don't have, I don't know, like, so yeah, the relationship is there is none. Any other questions regarding the logs? Okay, next thing. PCRs are a limited resource, right? Like there are 24 of them, and of those 16 are available, like are regular PCRs, and of those 8 are kind of taken by early boot. And then if you discount IAMA and the other things, basically user space has 4, and Systemd took all 4 of them to measure things like the machine ID and the boot phase and things like this. So what's left are now 0 PCRs for any further users. That's very little. So the thing though is that TPMs actually have this, you know, PCRs are in a way a legacy concept. They only have them because TPM 1.2 had it. They actually have a much more powerful concept these days, which are these already mentioned NV indexes, which are a little bit of memory that are named after a number and that you can store stuff in there. These NV indexes have a couple of types. One type is basically the PCR type, which you can use to make an NV index work like a PCR. So this has been theory for most of Linux existence. And I recently added to Systemd the concept, well, it's not merged, it's a PR because of, I will explain why. So that we can measure not just into PCRs, but into NV index-based fake PCRs. So they have the same semantics, right? Like that they, I mean, it's very confusing actually because NV, right, that stands for non-volatile, right? Like, so a PCR, however, is inherently volatile, right? Like, because it's supposed to start at 0 at boot. So with these special PCR like NV indexes, they came up with this model where you basically statically, persistently allocate a thing that you call non-volatile, which has a property that is inherently volatile because it always starts at 0 at boot. Very confusing. So to make this even more confusing, because I have trouble saying static NV index, because I have trouble saying NV index backed PCRs, inside of Systemd we decided to call them NV PCRs, right? Which is bogus, of course, because they are not non-volatile, they are very much volatile. So anyway, what does this give us? There are many more NV indexes available than there are PCRs. So I think the TCG people call PCRs beachfront property because there are very few of them and they're very expensive and you should be very careful with how you use them and how you waste them. But with NV indexes, we have a little bit more. We don't have that many because cheap TPMs don't have that many, but we have at least more than 16. The NV indexes have one problem though. They don't have names, they are identified by a number. That's why they're called indexes. And this is highly problematic if you, I mean, you can just go to the TPM and ask it, hey, please assign a NV index to me, and then it will find a free number, or you have an algorithm where how you can find a free number and then you can use this. But once you have that number, you somehow have to communicate this to the earliest boot process, right? Like, because again, these measurements typically you want to start really, really early because the later components shall be able to rely on them. But how do you do this? Like, you allocate the number and then you have to, for the next boot, tell it during early boot. Like at a moment where storage is typically not available, it's a terrible mess. So I implemented this so that we can store this information in the ESP so that we can know it before the kernel initializes. And then I decided, oh God, this is all horrible. And I talked to the TCG people and they just said, you know what, we'll just assign a static NV index range to Systemd. So because they actually have a specification where it basically says, yeah, this NV index range belongs to Microsoft, this one belongs to, I don't know, Amazon and whatever else. And it's only by convention, but yeah. And then I said, well, great, let's do that. And they assigned a range to me, but then they came back and said, oh, we'd rather assign it to Linux so that they don't have to micromanage things between open source projects. And yeah, so now they're assigning an even larger range to Linux, which we maintain, intend to maintain as part of the UAPI group. So, I mean, the NV indexes have many uses. Like if anyone else from a generic Linux project needs a couple of NV indexes, just find that document then and ask us for that, and we can give you a couple that you can then exclusively own. If you own them, then this has a major benefit that you don't have to store, like pass around to early boot any information about which number to use, because you just know which number to use because it was statically assigned to you. So, if we have these NV indexes and can use them as additional fake PCRs, and all of that is implemented in Systemd. As mentioned, I already implemented all of that, but with the dynamic part, which I now going to strip out. Then we can start measuring a ton load of additional things without interfering with the measurements we already make. Like, for example, like one of the things that I implemented right away is that we can, the SM BIOS identity, which is like the UID of a system, which, like in particular in virtualized machines, it's kind of frequently used to pass a UID that identifies the system. It's kind of interesting to measure that because then you can bind policies to this. So that's something we added because now we have the ability to measure other things. And then in Systemd we have various concepts like system extensions, configuration extensions, which basically extends the system, and etc. with immutable, lockdown, signed additional file systems via OverlayFS. So we can measure those too as we apply them. We can measure portable services, we can measure nspawn containers, all of that invocation, so that suddenly we cover a lot more than just the boot process of a system, but we cover the entire runtime of the system. So basically anytime you start a container, anytime you start a service, there's a measurement made of the resources that this container or this portable service or whatever else you have entails. And that is fantastic for remote attestation, because at any point in time you can like from the measurement logs say which files are present on the system and how they came to be. Yeah, it's all in the measurements logs. And yeah, I kind of like this property for many, many reasons. Yeah, so we can measure more simply because PCRs are not quite as expensive anymore. Any further questions regarding these fake PCRs?
How do you order the service initialization if you measure them? And you have a multi-threaded bootup, then what is the final, this is my service set?
Okay, so the question was regarding parallelization of service startup. If we measure all services and we parallelize service startup, the order is kind of like not predefined, right? Like, so what does it mean for the measurements? So the thing is, you know, if you do measurements, there is value in having a predictable order. And this value is there so that you can predict the values after boot, for example, for unlocking a disk, right? So that is one use case of measurements. But this only is relevant to up to some point, right? Like it's for unlocking disks, so that you can predict during like a certain phase of boot what the PCRs will be, right? For service startup, right? I don't think that is really a like matters so much, right? Like because services get started, get stopped, get started, get stopped. It's a continuous thing. It's the use case isn't as strong for like you wouldn't lock disk encryption to it, right? Like you have no reason to predict so much. The use case for that, I think, is more about remote attestation, right? So in remote attestation, the order doesn't matter, right? Like, because you do not have to predict, you just look at what happened, not at what's going to be, but what happened. And then hence you can, in software, just accept that it doesn't matter in which way these two services got started, as long as they both got started, right? That is my more philosophical answer, right? Like, it doesn't matter. But like, if you actually do want to do this, right? Like, for example, because you actually want to lock your disk to two services having been started, you have two options, right? Like, either you, like in the PCR log case, for example, it gives you this possibility to have multiple versions of the same component. So you could use that to just allow both orders. Or, you know, what Systemd is really strong about is about giving you the ability, if you want to order services with after and before expressions in unit files. So if you want defined order, there you go. You have the knobs, just implement it. If you do not care about the defined order, you shouldn't be surprised, though, if you don't get this defined order, if that's a valid answer. Anything else to that stuff? Otherwise, we go to the next.
How the Systemd measure is measured in the previous stages. So because Systemd measure extended PCR, and so the user space component that do the measurements, how they measure themselves.
Okay, the question was regarding the user space component that actually does the measurements. How does it itself get measured? In my world view, the system is always built around DM Verity, right? So that all the, like, you know, at Microsoft, for example, we have this IPE LSM thing that is supposed to enforce that all code that runs on the system comes only from a certain set of DM Verity-backed file system. So if you have something like this, and you know that, hence you know and can enforce that code only can run from /user, which is DM Verity-backed, and during early boot you did a measurement of the DM Verity root hash, then you should be covered.
Okay, so it's the same also for file modification. So if you measure something, then this measure the file will not change. So because you measure some component, and what happens if the file is modified later?
Well, I mean, yeah. I mean, what's key is really that, yeah, the measurement, the measurement tool itself is already covered, and it is in my model. I didn't really understand the question though.
So you do measurements of some component, but then this component changes over the time.
Yeah.
How do you ensure that your measurement list is accurate or the?
Okay. So the question was regarding how to handle updates of components covered by the Systemd PCR log policy stuff. So I mentioned this that components can have multiple alternative gold measurements, and this is what you're supposed to use there, right? So you have a drop-in directory which has another subdirectory, one for each component, and then for the stuff that, for example, comes from the OS vendor, every time the OS vendor provides a new version, they should provide a new drop-in for this. And as long as they want to have the old version also supported, they have to keep the old gold measurement in there. And when they remove this directory, like this file from the directory, then it will be removed from the policy again. And every time they make changes to these drop-in directories, adding new alternatives, removing new alternatives, they have to rerun the Systemd PCR log utility. And it's written to be idempotent, right? Like, so it tries to really hard to not do things if nothing changed, right? Like, so the idea is basically call it whenever you even have the suspicion that something might have changed. And in the worst case, it just doesn't do anything, or in the best case. Like, what if a process does a...
Do writes a file that you mentioned before.
Like...
you have a process that do a write of a file, and this file is then used, but the modified file, not the one that you measured.
I mean, so the question was regarding what happens if I measure a file and then the file is modified? Nothing, right? Like, because that's not supposed to happen, you know, because you, like, what are we talking about? Well, like, what kind of file? If it's in /user, then it's Verity-backed, so you just can't that every file is immutable there, right? If we are talking about some file in /var, like, at least in our code, we currently do not measure anything there, but also one shouldn't misunderstand measurements, because measurements don't mean that some data is forever something. It just means that at that point in time, that data was that, right? And that's the claim we make. If you have stuff that changes, you have to figure out how you protect this, but we will not do this for you in any way. Anything else about the NVPCRs or anything else we talked about? Otherwise, yeah.
So what all components should be measured according to you? Like you mentioned, bootloader, operating system. I mean, what all services should be measured as a guideline?
Oh, so the question was regarding which components precisely should be measured. Like, measured should be everything, right? Like any kind of code that you have in the system and any kind of configuration in the system, I'm pretty sure we should measure it all, right? Like that the data is generally available. It's another question which components, like which measurements should actually be included in a real life policy, right? Because if you measure everything, then it gives you the freedom that whatever kind of object you want to lock against the TPM and against the measured stuff, you have the freedom to pick whatever you want from these things that you measured. And that highly depends on your use case, right? Like I mentioned this earlier, for example, in some use cases, like let's say I build a cashier system. I probably want to lock down, because it deals with money and things like that, I want to lock things down a little bit tighter than I would want on a, I don't know, gamer PC, right? Like in a gamer PC, I probably don't want to lock down the firmware configuration, but I still do want to lock down the actual OS code, right? While on a cashier system, you probably want to also not allow people to boot other stuff or something, so you want to kind of cover the firmware stuff as well. So this really highly depends on your use case. And in Systemd TPM lock, you basically get the flexibility to do this, right? Like because if you invoke the tool, it basically allows you to lock down components individually, right? Like, so it can basically generate a gold measurement for a specific bootloader version, which I think is probably what everybody should be using. It also gives you a command to lock down the current firmware configuration, right? And that's something that those who care about this kind of security should call, but not probably others. So I'm pretty sure there's a baseline of stuff that everybody should lock down, which is UKI, shim, bootloader, and a couple of user-space things or something. But if you want to, you can go to all extremes and lock down also the configuration. But of course, every time you lock down more, you might confuse your users if they ever change the tiniest bit of things, and they might get pissed at you because they can't unlock the disks anymore. Any other question at this time?
How do you handle caves, or do you prohibit it?
Oh, that's a very good question. I actually have this here on my slide here. This sucks. It's right here. I have no idea how to do this. No, I have some ideas actually. But let's come. Like, how much time do you have left? Like a lot of time. Okay, then let's come back to this later when we come to this slide. I mean, I don't have that many slides anymore, but anything to the stuff we already talked about. Any further questions about that? Otherwise, let me talk about the next thing first. So, what's also new, so as it turns out, TPMs are weird things. Like most people assume that they're kind of this part of the platform and hence are always accessible, right? Like you compile the drivers into the kernel and they're just there and everyone can just do his measurements. In reality, that's not like that because we nowadays live in a world where people have VTPMs and where people implement TPMs in TEEs and things like that. And like, for example, opt, like this ARM thingy exists. And you know, to implement a TPM properly, you need some kind of storage so that you can implement NV indexes and things like that. But if you need storage, then it's kind of hard to do that in some enclave or whatever you want to call this thing, because they generally don't have storage. So that typically then involves some user space component that takes the storage requests basically from that enclave or whatever you want to call that. So that kind of means that unless some user space components on the regular kernel runs, TPM functionality is not really available. Not in the general case. In the specific case, it is. Like, if you actually have a discrete TPM on a PC, then yes, you probably can get away with assuming it's always there. But in the general case, it's simply not there. So one thing we recently added is that there is a clear defined a synchronization point during the systemd boot up, which is called TPM2.target. It's basically a milestone. Once we reach that point, we can assume that TPMs are there. And everything that requires TPMs, like all the code that we do with measurement, all the code that we do with unlocking disks and everything else, is ordered behind that. It's actually really weird that we need to do this, right? Like, because many people, in particular kernel TPM people, kind of assume that TPM is always available and just can be talked to, but no, it's a thing that is in the initRD, usually where it suddenly becomes available. This even comes with, you know, depending on the distribution, some people put the kernel drivers, like the TPM kernel drivers, they compile them into the kernel. Some people use them as a kernel module. We support both, but we also have this big problem that if we boot up on a system, we need to determine, like, if it's worth waiting for a TPM driver to show up, like if it's worth waiting for def TPM RM0 to show up, or if we are in a system where it's never going to show up because there is no TPM, right? Like, because initially when the kernel initializes, it will not have an access to the TPM. So do we wait for one or do we not wait for one? And we address that with something called Systemd TPM generator, which looks at the firmware and then makes the assumption that if the firmware has seen a TPM and reported to the OS that it has a TPM, then we make the assumption that eventually the driver will also be loaded on the Linux side, and we can access it, and hence inserts the synchronization point explicitly so that we actually wait for it. Anyway, long story short, what I actually wanted to get across here is yeah, initialization of the TPM at some point is like, knowing when to use it is surprisingly complex, but we should be covering that nicely, in particular for a world where we have TEEs. Sorry?
You're basically using ICPI table, which is supported in the presence of TPM.
We're using what?
ICPI table.
Oh yeah, we're using the ICPI table. Actually, we're using two things. Like, one is the ICPI table, and then we use something. I don't forget the details, but we had to tweak it because not everything is ACPI and things like that. Anyway, so the last thing that I wanted to mention that we have now is multi-profile UKIs. I actually merged the last bit of that 2 days ago. You know, this entire model that we're building this Systemd TPM hookups on is based on the model that UKIs are a thing, right? Like these unified kernel images. But unified kernel images are restrictive, right? Like, you cannot just change them, because if you change them, then both the secure boot measurement, the secure boot signature and the expected PCR measurements are going to change, and then things go bad, right? Like, so they are a lot more like rigid than the current model is, how general purpose distributions do it right now. So what we recently added basically is, because we realized that in a lot of cases distributions want to have multiple different kernel command lines, for example, that they provide in the boot menu that you can pick from. Like, for example, one that is the debug one, which turns on debug logging or something, or one that is a rescue mode, a recovery mode, or one is the I don't know, factory reset mode, where they delete all the user's data and start from fresh, right? So we recently added this hence to our UKI concept, so that you can basically, a UKI can now contain several sets of combinations of kernel image, initRD, kernel command line, device tree, and the other resources it manages. And that the boot menu can extract this information and show you multiple entries, and you pick one. This, of course, has implications for measurements, right? Like, because it suddenly matters. We need to know which profile was actually measured, like picked, and then measure only the components that relate to that profile. Anyway, this, like, yeah, it's kind of fundamental to mention this, that because it adds a little bit of variability into a system that otherwise is very rigid and very specific, and probably lacks of the applicability to the general world. Anyway, this is all I have about what's new. on my last slide here, yeah, the problems that are still left to fix, that I still, like the big things on my to-do list, what I, right now, want to cover with all the TPM hookups. The first thing is the kexec and soft reboot thing. You know, yeah, kexec, everybody knows what that is, I presume. Soft reboot is this thing that we recently added to Systemd, where we basically can do a very, very quick reboot where we just shut down user space and then start up user space again. We use that in Azure and things like that to have really, really short gray out times, right? Like, because the kernel does not get reinitialized in this model, but all of user space is. Now, both kexec and soft reboot have major implications for TPM stuff, right? Like, because TPMs, they initialize the PCRs and fake PCRs to 0, of course, if you do like a power cycle. So if we don't power cycle because we just replace the kernel or because we just replace user space, then what does that mean? People have had lots of ideas. I think I know what I would do, but yeah, I mean, it creates a lot of problems. Like, for example, the policies that things are locked down with, like, for example, disk encryption policies, need to take into account that suddenly there are multiple iterations of the operating system that, from the TPM point of view, are just one boot. So we kind of have to express policies on all objects so that they can cover for this model. There are other problems that we have to deal with, like, for example, if you ever do remote attestation of a system that kexec or soft reboots, you need to have the full logs around of all the earlier boots as well. So yeah, we need to pass over like the entire boot logs, not only from the firmware to the OS, but suddenly from the OS to the next iteration of the OS and to the next iteration of the OS. There's other problems, like, for example, when we do a kexec or a soft reboot like this, we do need to measure something so that this is itself something that we can recognize in the measurement logs, and it should be something that identifies that iteration, and a couple of other things. I think some of these things are relatively easy to answer, and some of them are really hard to answer. The summary, though, is, at least in my head, I do not have a clear picture how this all should play out. But let's say I have individual ideas about some things, because you asked the question, right? I'm not aware of anyone who knows very clearly how this all should look like in the end. But yeah, my current thinking is that we make the iteration of the system recognizable in some way in PCRs, and then we use Systemd PCR log or something like that, so that whenever we shut down one of these user spaces, we prepare a policy that's going to work for exactly the next iteration of the running system. And then from there on, we do that again for the next one and the next one and the next one. So that basically, and there should always be a nonce included, so that basically the next operation, the next instance of that operating system can access its keys, but not any older one or next one or any other system. So that's kind of what I was thinking. I think, yeah, there are questions that are unanswered. It's like, yeah, like the question, like, yeah, I'd like to find that the most lockdown policy for this that we can come up with, that people still don't have to think about, if you understand what I mean. Anyone has to say anything about this? Who has already solved the kexec thing?
Maybe it goes along with your rotation of the measurement logs too.
Yeah. Like, I mean, the rotation of the measurement logs is like the next thing. I bitched a little bit about IMA not having this. We don't either. So maybe I'm a little bit unfair, but I think the difference is that right now we do not do high frequency measurements, right? Like most of our measurements at this point in time happen until, like, they basically settle once the system is booted up. As mentioned, now that we have the fake PCR, suddenly we can measure a lot more, and also during runtime, because services, containers, they start and stop and start and stop all the time. So this implies that we have to think about measurement logs, measurement log rotation. I think I know exactly what to do there. Yeah, we're just gonna probably keep the first part of the measurement logs always around, because they are useful to do predictions for disk unlocks. But then we're gonna remove everything in the middle and then replace it by a new record that contains the hash of the old one. And then we continue from there. So that's kind of what I have in mind. But this basically means that, yeah, we're gonna erase something once it's grown too large, but we're gonna pin it by the contents. And the assumption, though, that an orchestrator or whatever other component that does remote attestation has, of course, to keep around either the full logs or at least a record that validated the logs up to some point, so that it can deal with the fact that history is going to get missing. Because, yeah, if you don't do that, of course, yeah, you can't prove that the system is in order anymore. Yeah, I think I know exactly what to do, and I think it's probably not hard to do. But yeah, I think this is like unlike the chi-exec problem, I think it's a much more I don't know, at least in my head, solvable problem.
Do you think that some parts of that in the middle you could find patterns and then compress in the sense of, hey, this kind of cycle of process thing sort of repeats n times? Do you see? I don't know exactly what you went through measuring, but do you see patterns occurring there that could be more easily replicated?
So the question was regarding whether if we delete something, we can instead try to find patterns and then basically compress, I guess is what you would call this. I mean, sure, you could do this, but I'm pretty sure like if you just gzip the file, it's going to be much better than anything we try to be smart about. And sure, we can do this, but I mean, it has it's not going to solve the problem. It's going to delay the problem, but it's not going to solve the problem. So we just have to deal sooner or later with the fact that we cannot for all eternity. I mean, one solution to this thing is, of course, say, yeah, after a week we reboot, right? Like, which I guess is the answer right now to IMA measurements, and then everything starts new. But of course, this is for many people not an acceptable solution, right? So yeah, I think we have to deal with the fact that, yeah, we have to kill log things, and then we have to do this in a way that, yeah, as verifiable as possible. And I think if we insert that record that has a hash of what we removed, we get as good as we can be. Anything else? Anyone has anything to say about this? So the very last thing I wanted to talk about is, so one little project that I have is, so I'm not sure anyone has heard about Systemd confaxed. Like Systemd confaxed is the component that we added to Systemd, which is how I personally think that configuration management should happen. And what it actually does is it's basically a tool that helps you apply DDIs. Like DDIs are these DM Verity protected file system images. Like DDI stands for Discoverable Disk Image. It's like an acronym we came up with, but we kind of try to push everyone to use DDIs for everything. It's basically a GPT partition table that consists of a file system of DM Verity data and of a little partition that contains signatures for the Verity data. Anyway, so confax is basically a way how we can set up such a DDI that contains configuration, and then we use overlayFS to apply one or more of these onto etc. So the idea basically is that if you want to, on a node, deploy some configuration files or, I don't know, key material or whatever else, you prepare one of these DDIs, you give it to Systemd confax, and it will just overlay it over etc. And the files in these confax DDIs will then either be there when the thing is applied or gone. So it has this nice atomic behavior, it tracks ownership, and yeah. And it's entirely backed by DM Verity, so you can always afterwards like figure out where a file came from, right? Like you can cryptographically say that. So confax is of course awesome, but we can, I think, make it more awesome if we actually link that now to remote attestation. So I kind of want to go to this model where, let's say, in like a central orchestrator, whatever you want to call it, that manages a couple of nodes, can read the remote attestation reports from the individual systems, and can then turn that into a confax basically for new configuration for these individual nodes that logs against the precise PCR measurement at that time, right? Like, so a node sends to the orchestrator a quote covering the PCRs and the relevant measurement logs. The orchestrator analyzes that these logs matches the PCRs and that everything in the logs actually is a valid component that the node was allowed to use. Then after it verified that, it basically figures out new configuration for that node, turns that into a convex DDI, like one of these disk images, and now attaches a TPM policy to that makes sure that only that specific node that actually has, according to the PCR values and NVPCR values and everything, is still in that state that it just analyzed, can apply them. Like, and this is then the DDI this generates, you pass to the node again, you apply there on etc, and suddenly this will only work if it's the actual node that this was intended for, and if the node is still running that software and that configuration and the state and everything else that it was supposed to have. So for me, this is like the ideal way how to do like distributed configuration management in a completely locked down and secure way. And you can even make it fancy with including like time-based policies and things like that, so that you can basically give a time window when you can apply it. And this is good enough to do key deployment as well. So this is kind of the ultimate model that I want to go for, that the attestation is good enough for something like that. And again, like most of the components to make this happen, we already have, right? Like with convex exists, and PCR log actually does all the log analysis for this, and we have all the TPM policies for most of what I was just talking. So, but it's still like an effort of gluing in a couple of missing bits. Like the big things are all done. It's more about gluing it together that something like this can work. So in my perfect view, this is how configuration management should be done, and is my answer to things like, I don't know, Ansible and Chef and whatever they're all called, but suddenly in a super secure, atomic, lockdown way. Just to give a little bit of a background, like what the problems are that I think we still need to address. And that was kind of my last slide. So anyone else has any questions? Like, how much time do we still have? Okay, no one has any questions. Did anyone even get what I was saying here? Usually if nobody asks questions, it means nobody understood it. But then again, a lot of people did ask questions. Matthew.
So you've been talking a lot about how to collect data, and you've been talking a lot about how a lot of this data makes sense in the context of remote attestation. Do you have a set of best practices about how people should interpret that data in order to avoid being confused by where are lines you say gain access to a system and then create additional log events without doing any Systemd stuff ahead of the log? How should whoever's consuming the remote attestation data be interpreting things in order to avoid things like that?
So the question was regarding like if there's any guideline or so for people who want to analyze the measurement logs that we provide, given that anyone is soon supposed to be able to insert additional measurement events into that, right? Like, what are the guidelines to avoid confusion in log analysis? So my answer to that is, so I think, you know, for the firmware measurements, it's kind of hard to do this properly, right? Like, because there are a couple of firmware measurements that you can interpret in multiple ways, and the event logs that is kept by the firmware is ambiguous about them and contains fields that you cannot find in the PCRs. My answer to that, if you add your own stuff, and we probably will enforce that in this little API that we will provide you with, that you can add in, measurements with, we can just include implicitly in the data that we hash, right? Like, you give us basically some hash of your data you want to have measured, and then we're going to augment it with a little bit of meta information about you, right? Like, so we take the stuff the kernel gives us about you, like your C group ID, your UID, like your PID, like the QCred data basically, and include it in the stuff that we actually measure, right? And then, because that uses a strong hash, the resulting thing should avoid any further ambiguities, right? So that's my answer to this, right? Like, because, yeah, I mean, I think one of the mistakes that the TCG did is that it measures fixed strings in multiple different contexts in multiple different places without encoding also the information about this context in this. And that basically means if you look at the event logs, you see a lot of measurements that look exactly the same. And that's where the ambiguity comes from. But yeah, the way to address this is to de-ambiguitize or something. And I think we can just do this implicitly for you, as long as we, in the event log, tell you about what we actually measured.
But this does depend on it not being in a situation where untrusted code is able to do its own measurements.
Sorry?
This is dependent upon there not being a situation where untrusted code is able to do its own extensions.
So, Matthew mentioned that this trusts on the fact that... no, what?
If I was watching TPM, if I could access the log file, I could do this without going through your API. So you're still dependent on that situation not arising if I want to be able to trust the logs.
So I mean, right now, like access to the TPM is relatively unrestricted, right? I think like the IPC thing, I don't know, like the event log we make world readable, I think. No, we don't actually make it world readable, but that has mostly to do with file logs, not because we wouldn't want others to access that. But so yeah, anyone can measure anything. That is true. But I talked to this with a couple of people earlier today, whether we should have a kernel interface where you basically tell the kernel to do the measurement for you, and the kernel basically does what I was just saying, that it implicitly adds some meta information that it knows. Yeah. So, like. The more complex answer to this, though, is that, you know, once we have NVPCRs, NVPCRs are a lot more powerful than regular PCRs because we can actually attach policy to it. So my intention was always that this meta information that we store is not stored necessarily only or at all in the PCR that you actually want to measure into, but there's basically the second log kept that is protected with an additional policy, like let's say with a nonce or whatever else that only the measurement tool knows, that stores the meta information about that something was measured there, right? So you have a two-level thing, and one of these things are, yeah, everybody could fake that, but the other thing then protects that, if that makes any sense. But I don't know if it makes sense, right? Like, because then you might as well not do the first measurement or something like this. So I don't know. Like, this is, I'm going forth and back about this. At least initially, I don't know. Like, I think access to dev TPM should be restricted to. I mean, it is restricted to privileged code, right? So that's my easy answer out. Just let the operating system do its thing. Of course, I think in the long run we should have tougher protections there, but I would always say these protections should be implemented by means of TPM policy and never by filtering, by the way, which is actually referencing to your stuff about resettable PCRs and process stuff. Anyway, let's talk about that somewhere else. Anyone else has any questions? There's a question.
My understanding is that Systemd uses index for PCR-like extension, and you talk about remote attestation. The problem is during remote attestation, you don't trust the event log, you trust the quote that has been signed by the TPM. How do you think you will provide a quote that is representing one Systemd execution implement?
So the question was regarding like if you do remote attestation, you need the quote and the event log, and how do you trust the event log? The thing is, the quote covers the event log.
I know the quotes cover the event log, but with Systemd's in-the-index PCRs, you don't extend those extensions. You don't write this extension in the TCG event log. So
Oh, we do. Like, no.
You extend them in the TCG event log too. Okay, so we can basically trust the quote of the TPM and then trust the whole event log. But if two event logs, like you said. How can I trust the second event log if Systemd is providing a quote of the second event log?
So Systemd is well aware of the UFI event log, right? Like we consider that as the continuation of our event log. So like quotes are actually a complex thing, right? Like because there's the TPM quote command, but we're probably not going to use that because it only covers PCRs and has various other issues. So there's like I talked to one of the TCG people about this. So there's another mechanism where you can basically fire a couple of things where you read PCRs and you get a hash of what you just read and can get that signed. And that's what we're gonna use. We will, like my assumption is that eventually we will have a little tool in Systemd called Systemd report or something like this, which is going to first of all get you one of these quotes from all the PCRs. Then it's going to go to the firmware event log and to our Systemd event log. It's going to synchronize that, right? Like so that this actually matches up. And then it's probably going to augment this data with, I don't know, some system state or something like this, and use that in the auxiliary hash thingy there, so that it's also pinned by the quote. And then you basically get a report back, which cryptographically proves to you the entire state of the system, both the current runtime state and all the historical state, and everything is pinned by the quote.
So maybe you can use TPM to get session digest that permits you to provide the quote. That is the quote of every command that has been executed in one session. So TPM provide the digest and quote it, so you assure yourself that.
Yeah, I think that might be the thing that we are gonna use, but don't press me on this because, like, I had a long phone call with one of the TGG people about this. Andreas Fuchs, by the way, great guy. In case he's listening in here, thank you very much for all the information. Yeah, that's what kind of like what you're saying there. Kind of sounds exactly like the stuff that he was telling me to use. And yeah, that's probably then what we're going to use. So it's going to be a lot of glue of collecting some stuff from the two logs that we care about, and then maybe pin some other stuff by hash, and then getting the TPM to sign all that, and then yeah. And then the analysis tool for all of this we already have, by the way, because that's what Systemd PCR log is, right? Like if we add a little bit of signature verification, then we have everything what we need in this area. So and then we can, yeah, provide a pretty comprehensive remote attestation thing, and then have this. I like, you know, the last thing that I was talking about, like where you have the reports thing flowing in one direction and the configuration in the other direction. I call that the cryptographical locked loop, right? Like because the orchestrator then, cryptographically can control the information flow in both directions. Anyway, it's the best thing ever. I think everybody should do it that way. And stopped. Like, because it's, because you can use it for just, for deploying secrets onto systems. It's an answer for so many different things. Because like all the clouds, for example, they try to distribute encryption keys for disk during early boot over the network and things like that. And suddenly, if you do it like this, then these kind of encryption keys just become information like everything else, right? Like you can just deploy them, like configuration like everything else. You can just deploy them with the same scheme. It doesn't really matter if it's early boot encryption keys or if it's late boot configuration. It's all the same mechanism and equally powerful and cryptographically secure. I don't know. I think my time's over anyway, but I still answer questions. But apparently no one has any. So then thank you very much for your interest.